Time seems like the simplest thing in the world. We measure it, chase it, live by it, every single day. But the deeper you look, the stranger it becomes. Scientists have discovered that time isn't what we thought it was. It bends, it stretches, it flows differently, depending on where you are and how fast you're moving. Reality isn't as straightforward as our clocks suggest, and the universe has been surprising us with how flexible time really is. In this video, we'll explore what time actually is, whether the universe even knows what time it is, and why the answer might change everything you thought you knew about reality. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. Time might be the strangest thing we take for granted. Every morning, we wake up and assume yesterday happened before today, that tomorrow comes after tonight, that the universe doesn't seem to care much about our schedules or our sense of when things should happen. Deep in space, where galaxies drift through emptiness, there's no cosmic clock ticking away, no universal timekeeper making sure everything stays synchronized. The atoms in your body are vibrating right now, trillions of tiny movements happening faster than you could ever count. Scientists use these atomic vibrations to build the most accurate clocks we have, devices so precise they wouldn't lose a single second over billions of years. Yet even these incredible machines aren't actually measuring time itself. They're counting changes, tracking how one moment transforms into the next. It's like trying to measure darkness by counting shadows. Think about the last time you were bored, really deeply bored, sitting somewhere with nothing to do. Minutes probably felt like hours. Your brain, deprived of interesting input, started paying attention to time's passage in a way that made it crawl. Now, think about the last time you were completely absorbed in something you loved. Hours vanished without a trace. The clock kept ticking at exactly the same rate, but your experience of time stretched and compressed like elastic. This flexibility of time isn't just something that happens in our minds. Einstein discovered that time actually does stretch and compress in the physical world, depending on how fast you're moving or how close you are to massive objects. An astronaut speeding through space ages more slowly than people on Earth. Someone living on a mountain peak, further from Earth's gravitational pull, experiences time slightly faster than someone at sea level. These aren't just theoretical possibilities, they're measurable differences that engineers have to account for when designing GPS satellites. Near a black hole, time becomes truly strange. The immense gravity doesn't just pull on matter, it pulls on time itself, stretching each second into something longer, thicker, almost viscous. If you could somehow survive near the edge of a black hole, you'd watch the rest of the universe speed up around you. Stars would be born and die in what felt like moments. Civilizations might rise and fall while you experienced a single day. But here's what's really puzzling. If time can slow down and speed up, if it's flexible and relative, what does that mean for the universe as a whole? Does the cosmos have some kind of master clock, some ultimate reference point for when things happen? Or is time just a local phenomenon, something that emerges wherever there's change and motion? The early universe gives us some clues. In the first moments after the Big Bang, when everything was incredibly hot and dense, the normal rules of space and time didn't quite apply yet. Temperature and energy were so extreme that the distinction between past and future became blurred. Particles popped in and out of existence. Causality, the simple idea that effects follow, causes, became tangled and uncertain. As the universe expanded and cooled, time began to behave more like what we're used to. But even now, 13.8 billion years later, time remains far from uniform. In the empty spaces between galaxies, where almost nothing happens for eons, time passes differently than it does here on Earth, where countless processes unfold every second. Chemical reactions, biological growth, planetary rotation, all the busy activity that makes time feel urgent and directional. Some physicists think time might be an illusion, a byproduct of how our brains organize information about the world. According to this view, the universe exists as a kind of eternal, unchanging whole, and our sense of moving through time, from past to future, is just how we perceive tiny slices of this larger reality. It's similar to how a movie seems to show motion and change, but is actually just a series of still frames played in sequence. Other scientists argue that time is fundamental, as basic to reality as matter and energy. They point out that every physical process we know about involves time in essential ways. Decay happens over time. Growth happens over time. Even light, traveling at the universe's speed limit, still takes time to cross distances. Without time, they argue, nothing could happen at all. The quantum world adds another layer of mystery. At the smallest scales, where individual particles interact, the normal flow of time becomes fuzzy. Quantum events don't follow the orderly sequence we expect from everyday experience. Effects can sometimes precede their causes, at least in certain limited ways that don't violate the overall structure of space-time. Meanwhile, the expansion of the universe gives time a kind of cosmic direction. As space itself grows larger, carrying galaxies away from each other, it creates what physicists call an arrow of time. The universe is becoming less dense, less organized, more spread out. This gives us a universal sense of forward progress, even in regions where nothing much is happening locally. But does the universe actually experience this passage of time, or is it just something we project onto the cosmos from our particular perspective? After all, we're embedded in time so completely that it's hard to imagine what timelessness would even mean. Every thought you think, every breath you take, every heartbeat happens within time's framework. Consider how memory works. Your brain stores traces of past experiences, creating the sense of a personal timeline stretching backward. But these memories exist right now, in the present moment. The past they seem to preserve isn't actually there anymore. It's just patterns of information encoded in neural networks. Similarly, your ability to plan and anticipate creates the impression of a future that's somehow already waiting for you. But that future doesn't exist yet, either. It's just possibilities your mind constructs based on present conditions. This makes you wonder whether the universe needs memory or anticipation, the way we do. Does it remember the Big Bang? Does it anticipate heat death? Or do these concepts only make sense from our limited viewpoint as creatures who experience time as a flowing stream rather than seeing it all at once? The strangest possibility is that time might work differently in different parts of the universe. In regions where space itself is twisted by extreme gravity, time could loop back on itself, creating closed curves where cause and effect become circular. Near rotating black holes, space-time gets dragged around like honey, potentially allowing for paths through space and time that connect different eras. Some solutions to Einstein's equations suggest that the geometry of space-time could theoretically allow time travel, at least in principle. This doesn't mean it's practically possible, but it shows how flexible time can be when gravity becomes extreme. The universe seems to allow for temporal structures that our everyday experience can't even imagine. Yet for all these exotic possibilities, time remains remarkably consistent in our local neighborhood. The Earth rotates at a steady rate. The sun burns through its nuclear fuel on a predictable schedule. Radioactive elements decay according to precise mathematical laws. This reliability is what allows life to exist and evolve, what makes chemistry and biology possible. Without time's steady progression, there could be no growth, no learning, no adaptation. Every living thing depends on time's passage to function, from the rapid firing of neurons to the slow accumulation of evolutionary changes across generations. We're not just observers of time, we're participants in it, creatures whose very existence depends on temporal processes. This makes the question of whether the universe knows what time it is both profound and personal. Because if time is just a human construction, something we've invented to make sense of change and causality, then asking whether the universe experiences time might be like asking whether it experiences color or music. These could be qualities that only emerge when matter organizes itself into complex patterns, like brains and nervous systems. But if time is fundamental to reality, woven into the fabric of existence itself, then perhaps the universe does have its own relationship with temporality, something far grander and more encompassing than our small-scale experience of seconds and minutes and years. The universe operates by rules that feel solid until you examine them closely. Then everything starts to shift beneath your feet. Consider what happens when you place two perfectly identical clocks in different situations. One remains here on Earth's surface while the other travels on a high-speed journey, or gets positioned far from our planet's gravitational pull. When these clocks reunite, they will disagree about how much time has passed. This disagreement isn't caused by mechanical failure or poor craftsmanship. The clocks experience time at genuinely different rates because time itself flowed differently in their separate environments. Einstein's relativity theory predicted this strange behavior decades before we could measure it, and every experiment since has confirmed the prediction. Time refuses to behave like the universal constant we imagine it to be. Instead of acting like a cosmic metronome, keeping steady rhythm across all of space, time bends and stretches according to speed and gravity. This flexibility shapes everything around us in ways we rarely notice. The satellites orbiting overhead right now are experiencing time at a slightly different pace than we are down here. Without constant adjustments to account for this difference, navigation systems would become increasingly inaccurate, drifting off course by kilometers each day. Even tiny changes in elevation create measurable time differences. The top floors of tall buildings age just a fraction faster than the ground level. Your head, being slightly farther from Earth's center than your feet, experiences time at a barely detectable but real different rate. These aren't abstract mathematical curiosities. They're the actual mechanics of reality operating around us constantly. When we wonder whether the universe knows what time it is, we're immediately confronted with a deeper problem. Which time are we talking about? Time measured where? According to whom? The question multiplies rather than simplifies when you dig into it. This leads us toward a more fundamental insight about the structure of everything. Space and time aren't separate entities that happen to coexist. They form a single interconnected fabric called space-time. Mass and energy cause this fabric to curve and bend, creating what we experience as gravitational effects. These curves don't just influence the paths objects take through space, they also determine how quickly time passes in different regions. Standing on Earth's surface, you're not simply being pulled downward by some mysterious force. You're resting in a curved region of space-time. That curvature affects every clock, every process, every moment of duration in your vicinity. The geometry of space-time around you is constantly shaped by the mass of the planet beneath your feet, the sun in the distance, and every other object with energy or mass anywhere nearby. But this geometry isn't fixed or permanent. It responds dynamically to whatever happens to be present. Move to a different location, change your speed, alter the distribution of mass around you, and the flow of time shifts accordingly. This creates a universe where different observers can legitimately disagree about fundamental aspects of reality, including when events happen and in what order. We typically experience time as a smooth, steady progression, one moment following another in an orderly sequence. This feels like the natural state of things, a universal truth that applies everywhere equally, yet this sensation of uniform time flow is actually quite local and specific to our particular circumstances. Other observers moving differently or located in different gravitational environments have their own equally valid experience of time's passage. The concept of simultaneity, the idea that events can happen at the same moment across different locations, becomes problematic when you account for relativity. What appears simultaneous to you might occur in a different sequence for someone else, and both perspectives are equally correct according to the laws of physics. This means there's no universal now moment that applies throughout the entire cosmos. This absence of a shared present moment challenges our intuitive understanding of reality. We naturally assume everyone experiences the same current moment, that there's some cosmic clock keeping time for the entire universe. Instead, physics reveals a reality where time is personal and local, tied to your specific motion and position within the fabric of space-time. In regions of space far from stars and planets, where matter is sparse and motion is minimal, interesting questions arise about time's existence. Does time continue its steady progression in these empty regions, or does it require the presence of matter and change to have any meaning? The geometry of space-time extends throughout these apparently empty regions, suggesting that time remains present even when nothing seems to be happening. However, without any processes to mark time's passage, without observers or clocks or changes to measure, time becomes effectively invisible. It may exist in principle, but remains undetectable and unmeasurable. This raises deeper questions about whether time requires witnesses to be meaningful, or whether it maintains its reality even in complete isolation. Some theoretical approaches suggest time might not be a fundamental feature of reality at all. Instead, it could emerge from more basic processes involving quantum mechanics, particle interactions, or the tendency of systems to become more disordered over time. These ideas propose that time isn't something the universe possesses inherently, but rather something that appears when certain conditions create patterns we interpret as temporal flow. If time is indeed an emergent property, rather than a foundational aspect of reality, then asking whether the universe knows what time it is becomes almost meaningless. The universe wouldn't need to know the time, because time wouldn't exist as a basic feature requiring knowledge or tracking. This perspective forces us to reconsider our most basic assumptions about the nature of reality. We're accustomed to treating time as obviously real, constantly present, and universally applicable, yet careful examination reveals something far more subtle and complex, something that defies simple explanation or universal measurement. Even the directionality of time, our strong sense that past becomes present, becomes future, isn't clearly mandated by fundamental physical laws. Many equations describing natural processes work equally well, whether time moves forward or backward. The universe itself seems indifferent to temporal direction, yet we consistently experience time flowing in one direction only. This creates a puzzle about why our experience of time feels so definite and universal, when the underlying physics suggests something much more flexible and observer-dependent. Perhaps our perception of time's steady forward flow is more about how our consciousness processes information than about time's true nature. The question of what time really represents becomes increasingly difficult to answer as you examine it more closely. If we can't define it precisely, measure it universally, or even agree on basic facts about its flow and direction, then what kind of phenomenon are we dealing with? This doesn't make time illusory or unimportant. It just suggests that time might be fundamentally different from what our everyday experience suggests. Right now, as you rest in your particular location, you're experiencing time at a rate determined by your specific circumstances, your elevation, your motion, your position within Earth's gravitational field. Someone elsewhere in the universe is having their own temporal experience, their own rate of time passage, shaped by their own unique situation. Neither experience is more correct or fundamental than the other. Both represent valid ways that time can behave under different conditions. This variability isn't a flaw in how time works, it's an essential feature of how reality is constructed. The flexibility of time, its dependence on circumstances, its refusal to behave uniformly, these aren't problems to be solved but characteristics to be understood and appreciated. When we return to the original question about whether the universe knows what time it is, a different kind of answer begins to emerge. Perhaps the universe doesn't need to know a single, definitive time because no such time exists. Instead of seeking one universal temporal truth, we might need to accept that time is inherently multiple, local, and dependent on perspective. This multiplicity isn't a limitation, it's simply how time operates in a universe, governed by relativity and shaped by the dynamic interplay of matter, energy, space, and motion. When you check your phone for the time, you're participating in something that feels completely natural. Every clock around you seems to agree, ticking away at the same steady pace. But this agreement, this shared rhythm, only works because we're all moving slowly, sitting in roughly the same gravitational field. Step outside these ordinary conditions, and clocks start telling different stories, even when they're working perfectly. Take 2 atomic clocks, the most precise timekeepers we know how to build. Designed, sync them up, so they tick in perfect harmony. Now put one on an airplane and leave the other on the ground. After the plane lands, those clocks won't match anymore. The flying clock will have ticked away slightly less time than its earthbound twin. We're talking about tiny fractions of a second, but the difference is real, measurable, and happens every single time. You don't even need an airplane to see this effect. Sensitive clocks placed on mountaintops tick differently than identical ones at sea level. The change in altitude, the slight difference in Earth's gravitational pull, that's enough to make time itself flow at different rates. It's as if the universe has countless invisible neighborhoods, each with its own personal relationship with time. Einstein's theories explain this strange behavior. When something moves very fast, especially approaching the speed of light, time slows down for that moving object compared to something standing still. And gravity does something similar, bending not just space but time along with it. The stronger the gravitational field, the slower time moves within it. This isn't just theoretical physics. Your GPS system has to account for these time differences constantly. The satellites orbiting overhead experience slightly weaker gravity than you do on Earth's surface, so their clocks tick a bit faster than yours. Without correcting for this difference, your phone could place you miles away from where you actually stand. The technology in your pocket works because engineers take Einstein's strange universe seriously. Imagine an astronaut hovering near a black hole, staying just outside that point of no return we call the event horizon. From the astronaut's perspective, everything seems normal. Their heart beats, their thoughts flow, their watch ticks steadily, but someone watching from far away would see that astronaut's time crawling along like thick honey. The distant observer's clock might tick hundreds of times while the astronaut's ticks just once. If that astronaut fell past the event horizon, something even stranger would happen. To them, they'd continue falling inward, experiencing time normally, but to the distant watcher, the astronaut would appear to freeze at the black hole's edge, their final visible moment stretched out forever, never quite disappearing. From the outside, it would look like time had stopped completely for the falling astronaut. This reveals something profound about reality. There is no master clock running the universe. No cosmic timekeeper ensuring everything stays synchronized. Your now and someone else's now aren't guaranteed to line up, especially if you're moving differently or experiencing different gravitational fields. Even light, which travels at a constant speed through empty space, doesn't give us a universal timeline. When you look at stars, you're seeing ancient history. That starlight has been traveling for years, decades, sometimes millions of years to reach your eyes. You might be admiring a star that died long before humans existed, its light only now completing its journey to Earth. The farther apart things are in the universe, the harder it becomes to say what's happening. At the same time, distance and motion scramble our usual ideas about simultaneity. Two events that seem to happen together from one viewpoint might appear separated in time from another perspective. This is why physicists talk about proper time, the time measured by a specific observer following their own path through space and time. It's not universal, it's personal, shaped by where you are, how fast you're moving, and what gravitational forces surround you. Your wristwatch isn't wrong. If it doesn't match mine, it's just telling the truth about your particular experience of time. Think of it like living in a vast city where every block has its own time zone. You could step across a street and suddenly be a few seconds ahead of the person next to you, not because you skipped forward, but because that patch of sidewalk exists in a slightly different temporal flow. In everyday life, these differences are too small to notice, but they're always there, woven into the fabric of reality. In extreme environments, near neutron stars or at the edges of black holes, these time differences become dramatic and unavoidable. We've measured them in particle accelerators, watched them play out in the behavior of fast-moving subatomic particles, observed them in how light bends around massive objects. Every experiment confirms the same unsettling truth. Time flows differently depending on where you are and what you're doing. Some regions of the universe have experienced more time than others, not because they're older, but because space-time has treated them differently. Parts of the cosmos have aged at different rates, Like trees in a forest where some have endured long winters while others basked in eternal summer, this multiplicity of time might feel disturbing at first. We're used to thinking about history as a single story, a shared timeline that connects all events. But the universe operates on countless intersecting schedules instead. When we ask, "What time is it?" we're really asking, "What time is it here for me right now?" There's something liberating about this realization. Time isn't rigid or absolute. It's flexible and local. It moves with you, adapting to your path through space and the gravitational fields you encounter. There's no cosmic authority making sure all the clocks stay synchronized, because the universe doesn't care about schedules. It cares about relationships, about how things influence each other, how mass affects motion, how events connect across space and time. You exist within this web of interconnected timelines. Your heartbeat, your thoughts, your memories, all flow according to your personal temporal rhythm. And that rhythm is uniquely yours, carved out by your position, your motion, your place in the universe's gravitational landscape. Your experience of time isn't wrong just because it doesn't perfectly match someone else's. Your future isn't locked onto rails either. Your personal timeline can curve, stretch, slow down, or speed up depending on the choices you make and the paths you follow. Time becomes not just the stage where your life unfolds, but an active participant in your story, bending and flowing around you like water around a stone in a stream. When we think about empty space, we imagine a void where nothing happens, where time just ticks along at its steady pace. But space isn't really empty at all. It's filled with something we can't see, something that shapes how time itself behaves. This invisible fabric responds to mass, to energy, to motion in ways that seem almost impossible. Consider the clocks around you right now. Your watch, your phone, the atomic clocks that keep our world synchronized. They all assume time flows the same everywhere. But that assumption breaks down when you start looking closely. A clock sitting on your kitchen table experiences time slightly differently than one placed on your roof. The difference is tiny, almost nothing, but it's real. This happens because your kitchen clock sits deeper in Earth's gravitational well. Gravity isn't just a force pulling things down, it's a curvature in the structure of reality itself, and when space curves, time curves with it. The stronger the gravity, the slower time passes compared to regions where gravity is weaker. We discovered this through the most precise clocks humans have ever built, atomic clocks that can measure time to billionths of a second. Scientists placed identical atomic clocks at different altitudes and waited. After days of careful measurement, the results were clear. The higher clock ran faster, not because it malfunctioned, but because time itself flowed faster at that altitude. This discovery changed everything about how we understand the universe. Time isn't the constant backdrop we thought it was. It's more like a river that flows at different speeds depending on the landscape it moves through. Near massive objects, this river slows down. In empty space, far from any gravitational influence, it flows faster. GPS satellites experience this every moment they orbit Earth. They circle our planet in a weaker gravitational field than we experience on the surface. Their onboard clocks tick roughly 38 microseconds faster each day than identical clocks on the ground. Engineers program this correction into every GPS receiver. Without this adjustment, your phone's map would be wrong by several kilometers within hours. The philosophical implications are staggering. If time flows differently in different places, then the entire universe doesn't share the same moment. There's no universal now that connects everything. Each region of space experiences its own present, its own rate of change, its own timeline. Black holes take this concept to its extreme. These aren't the cosmic vacuum cleaners of science fiction. They're regions where matter collapsed so completely that space-time curves beyond our everyday experience. Around a black hole, time doesn't just slow down slightly. It can nearly stop altogether from the perspective of a distant observer. Imagine watching a friend fall toward a black hole. From your safe distance, you'd see something remarkable and disturbing. Your friend would appear to slow down as they approached the event horizon. Their movements would become more and more sluggish. Eventually, they'd seem frozen at the edge. Their image red shifted and fading, but never quite disappearing. Meanwhile, from your friend's perspective, nothing unusual would happen. Their watch would tick normally. Their heart would beat at its regular rhythm. They'd fall through the event horizon in what feels like a reasonable amount of time, but your timelines would have diverged completely. Hours for them might correspond to years or centuries in your reference frame. This isn't just theoretical anymore. We've observed stars orbiting the massive black hole at the center of our galaxy. These stars move at incredible speeds, sometimes reaching 10% the speed of light. When they swing close to the black hole, we can measure how time dilation affects the light they emit. Their orbital periods, their brightness variations, everything confirms that time really does slow down in strong gravitational fields. The mathematics behind this phenomenon emerged from Einstein's general relativity over a century ago, but we're still discovering new ways it affects our understanding of reality. Gravitational waves, ripples in space-time itself, carry information about how time and space bend and flex as massive objects collide billions of light years away. When we detect these waves, we're not just hearing the universe's most violent events, we're listening to time itself being stretched and compressed as space-time rings like a bell. Each gravitational wave carries a timestamp that depends on the path it traveled and the gravitational fields it passed through. This leads to a curious realization about the nature of existence itself. Every moment you experience is unique, not just to you personally, but to your exact location in space-time. The second you just lived through was shaped by your altitude, your velocity, your proximity to massive objects. Someone else, somewhere else, experienced a different second entirely. On Earth, these differences are minuscule. You'd need atomic clocks to detect them. But in the broader universe, the variations become dramatic. Time near the surface of a neutron star passes significantly slower than time in the void between galaxies. A day on a planet orbiting close to a massive star might correspond to years or decades on a world in a quieter region of space. This reality challenges our deepest intuitions about cause and effect. If different regions of space experience time at different rates, then simultaneous events aren't truly simultaneous. The concept of simultaneity itself becomes relative, dependent on your frame of reference. Early in the universe's history, when everything was much denser and hotter, time dilation effects were far more extreme. The expansion of space itself influenced how time flowed. Different regions of the primordial universe aged at different rates as density fluctuations grew into the cosmic web we see today. Some cosmologists speculate that in the far future, as the universe continues expanding and cooling, different regions might become so separated that their timelines diverge beyond any possibility of synchronization. Island universes, each ticking to its own temporal rhythm, connected only by the fading light of their distant past. We live in one thread of this cosmic tapestry, experiencing our local version of time while the rest of the universe marches to billions of other beats. Your heartbeat, the Earth's rotation, the Sun's fusion, the galaxy's rotation, they all contribute to the gravitational environment that shapes your personal timeline. Understanding time dilation doesn't just change physics, it changes philosophy. It suggests that time isn't something we move through, but something we're embedded in. We're not passengers on time's river, we're part of the water itself, flowing at rates determined by the cosmic landscape around us. In the deepest reaches of space, where galaxies thin out and stars become distant pinpricks, there's a profound silence that stretches for billions of miles. These regions feel abandoned, forgotten by the universe itself. Yet, something remarkable happens in these seemingly barren voids, something that challenges our basic understanding of existence. Imagine drifting through such a place, where the nearest star is so far away its light takes centuries to reach you. Here, in this cosmic wilderness, Particles of hydrogen drift lazily through the darkness, sometimes going millions of years without encountering another atom. These lone wanderers carry with them a strange truth. They're still aging, still changing, still marking the passage of time in ways we barely comprehend. The fabric of space-time itself doesn't vanish just because things get quiet. It remains stretched across these empty regions, holding its geometric patterns intact. Time continues its steady march forward, even when there's no clock to measure it, no observer to witness it. This persistence reveals something fundamental about the nature of reality. Time doesn't need permission to exist. When we send spacecraft into these distant regions, their onboard computers continue counting seconds with mechanical precision. But those seconds unfold slightly differently than they do here on Earth. Away from our planet's gravitational embrace, time actually moves a bit faster. The deeper you sink into gravity's well, the more time slows down. Out in the interstellar void where gravity's grip is weakest, time flows more freely. This creates an interesting paradox. The most active, energetic places in the universe, where stars burn and planets orbit, are also where time moves most slowly. Meanwhile, in the quietest, most seemingly lifeless regions, time rushes forward at its quickest pace. It's as if the universe has an inverse relationship between activity and temporal speed. Consider what happens when starlight travels through these empty stretches. A photon, leaving a distant star, begins a journey that might last millions of years, crossing vast expanses where matter is so sparse that entire solar systems could fit in the gaps between atoms. That light doesn't pause or rest during its journey. It maintains its constant speed, marking time's passage across the cosmos. The measurement of this journey gives us profound insights. Light from our sun takes 8 minutes to reach Earth. From the nearest star, over 4 years. From distant galaxies, billions of years. Each measurement confirms that time operates consistently across these seemingly empty regions. The light itself becomes a messenger, carrying information about when it was emitted and how long it took to arrive. But this raises a deeper question about the nature of time itself. We often think of time as flowing, like a river carrying us forward. Physics suggests something different, that we move through time, rather than time moving past us. Time resembles a dimension, similar to height or depth, providing structure and direction, but not motion in the traditional sense. In those quiet spaces between stars, when nothing seems to happen for eons, time continues mapping out possibilities. It maintains the framework that allows change to occur when conditions are right. Sometimes they are right. A particle of cosmic radiation, accelerated by a distant supernova, might streak through these regions at nearly light speed. Its journey obeys temporal rules, requiring time to complete its path. Even the background radiation from the Big Bang permeates these spaces, carrying timestamps from the universe's earliest moments. This ancient light has been traveling for nearly 14 billion years, stretched and cooled by cosmic expansion. We can measure its age, track its journey, decode the story of time embedded in its wavelengths. The comparison to sleep becomes illuminating here. When you rest, your body continues its work. Even though you're not consciously active, cells repair themselves, organs maintain their functions, time passes whether you're aware of it or not. Interstellar space exhibits similar behavior, appearing inactive while time continues its essential work behind the scenes. These regions aren't truly empty, despite their appearance. They contain the framework of space-time itself, curved and shaped by the distribution of matter and energy throughout the universe. Even where no matter exists, the equations of relativity still apply. Space retains its form, and form includes temporal dimensions. Think of the universe as an enormous theater. Most attention focuses on the brightly lit stage, where stars are born and die, where planets form and evolve. But even in the darkened wings, the theater's structure remains intact. The architecture continues supporting the performance, ready for action to resume when actors move into those spaces. Spacecraft venturing into deep space provide practical evidence of time's persistence. Left alone for decades or centuries, they don't remain frozen in temporal amber. Their components age, materials degrade, systems slowly break down. When we eventually reconnect with them, they've accumulated measurable time, aged according to their position in spacetime's framework. This aging occurs because particles naturally decay, even in the absence of external influences. Radioactive elements maintain their half-lives whether they're in a bustling laboratory or drifting through cosmic emptiness. Their decay rates provide universal clocks, ticking away in the darkness, where no human timepiece could survive. The persistence of time in empty space reveals something profound about cosmic architecture. Time doesn't require witnesses to exist, doesn't need events to validate its presence. It forms part of reality's fundamental structure, as basic as the dimensions of space itself. This challenges our intuitive understanding of time as something that emerges from activity. Gravity plays a crucial role in this cosmic timekeeping. Even in regions where gravitational fields are extremely weak, they still exist, still curve spacetime, still influence how time unfolds. A spacecraft in deep space still feels the distant pull of galaxies, experiences the subtle effects of cosmic expansion, participates in the universe's temporal symphony. The emptiest regions of space aren't paused moments in cosmic history. They're quiet movements in an ongoing composition, rest between notes that maintain the rhythm. When comets venture into these regions on their ancient orbits, they don't escape time's influence. Their paths unfold according to gravitational choreography that requires temporal coordinates to make sense. These insights force us to reconsider what emptiness means on cosmic scales. Space that appears vacant actually teems with invisible activity, quantum fields fluctuating, virtual particles appearing and disappearing, space-time itself maintaining its dynamic structure. Time provides the stage for these subtle performances. The question of whether the universe knows what time it is becomes more complex in this context. Each region maintains its own temporal relationship based on local conditions, gravitational environment, and energy density. There's no universal master clock, no cosmic timekeeper coordinating everything. Instead, time emerges from the collective behavior of spacetime's fabric. In these vast stretches between stars, time moves like an underground river, invisible but persistent, shaping the landscape even when no one observes its flow. It reminds us that existence continues in ways that transcend our immediate perception, operating on scales that dwarf human experience, while following the same fundamental rules that govern our everyday lives. Most of us picture time like water in a river, flowing steadily from past to future. It's the kind of image that makes sense, feels natural, fits with how we move through our days. But when you dig into the actual physics, that flowing river starts to look more like a complicated web. Here's something that might surprise you. The basic laws of physics, the ones governing how particles move and interact, they don't actually care which direction time goes. You could run the universe backward, and most of the fundamental equations would work exactly the same way. Picture two marbles hitting each other on a table. Whether you watch that collision forward or in reverse, the physics makes perfect sense either way. So why don't we experience time flowing backward? Why can't we remember the future instead of the past? The answer comes down to something called entropy, which is basically a measure of disorder. Think of it like this: there are way more ways for things to be messy than to be organized. Drop a coffee mug, and it shatters into countless pieces. Those pieces could, technically, all bounce back together and reform the mug. The laws of physics allow it, but the chances are so incredibly tiny that it never happens. This is where time gets its direction, not from some cosmic force pushing it forward, but from probability. Our universe started in a very organized, low entropy state. Since then, things have been spreading out, getting more random, increasing in entropy. That's why we see broken eggs but never unbroken ones spontaneously forming. But even this arrow of time isn't as simple as it first appears. When Einstein figured out relativity, he showed us that time isn't the same everywhere. Gravity can slow it down. High speeds can stretch it out. Two people can experience completely different amounts of time, while living through what seems like the same events. Imagine you're near a black hole while your friend stays on Earth. From your perspective, everything feels normal. But to your friend, watching from far away, you're moving incredibly slowly. Hours pass for you, while years pass for them. You're both experiencing time, but you're experiencing different amounts of it. This leads to something that sounds like science fiction but is absolutely real. All of space and time form a single, connected structure that physicists call spacetime. You don't just have a location in space, you have a location in time too. And just like you can take different paths through space to reach the same destination, you can take different paths through time. Here's where it gets really strange. If time is a dimension like the 3 dimensions of space, then past and future might both exist in some real sense. The moment you were born, the moment you're listening to this, the moment you'll fall asleep tonight, they could all be equally real, just located in different parts of the space-time structure. But you can only move through that structure in one direction. Your consciousness, your memories, your biological processes, they all flow forward. You can't rewind your thoughts or fast forward your heartbeat. You're stuck, experiencing one moment after another, even though the bigger picture might contain all moments at once. This creates a fascinating puzzle. If past and future both exist, what makes the present moment special? Some physicists think only the present is real, that the past disappears and the future hasn't happened yet. Others believe all moments exist equally, and our sense of flowing time is just a trick of perception. Quantum mechanics adds another layer of weirdness. Particles can become entangled, connected in ways that don't follow our usual ideas about sequence and timing. Measure one particle, and you instantly affect its entangled partner, no matter how far away it is. Not because information travels faster than light, but because both particles are part of the same larger quantum process. In these quantum systems, time doesn't behave like a flowing river at all. It's more like a network of connections, where events are linked in a web of relationships rather than lined up in a single sequence. Even at cosmic scales, the river metaphor breaks down. Different parts of the universe are aging at different rates. Galaxies in strong gravitational fields experience time more slowly than those in empty space. Some regions of the cosmos have fast clocks, others have slow ones. The universe doesn't tick to a single rhythm. This is why modern physics thinks of time less like a flowing substance and more like a geometric property of the universe. It's something that can bend, stretch, and curve depending on local conditions. You can move through it along different paths, accumulating different amounts of elapsed time depending on your speed and location. Your brain interprets all this complexity as simple forward flow, because that's how memory works. You remember the past, you experience the present, you anticipate the future, because leads to effect in a sequence that makes sense to your biological systems. But underneath that familiar experience, the structure of time is far more flexible. This flexibility opens up some mind-bending possibilities. If time is truly a dimension, then somewhere in the vast space-time web, there might be regions where entropy decreases instead of increases, places where broken eggs spontaneously reform, where scattered energy gathers together, where time, from our perspective, runs backward. These aren't violations of physics, just different paths through the same underlying structure. The math allows it, even if we never see it in our local corner of the universe. Our experience of flowing time emerges from the specific conditions we live in, the particular way our region of space-time is organized. What we call the flow of time is really just our path through a much larger, more complex landscape. Every step you take through that landscape is shaped by the structure around you, the gravity you feel, the systems you interact with. You're not drifting down a single river, you're walking one thread in an enormous web of possibilities. The universe we inhabit began in a state of very low entropy, very high organization. That initial condition set the stage for the particular arrow of time we experience. But it's not universal, not everywhere, not always. In some distant region of space, conditions might be completely different. creating a completely different experience of temporal flow. Time seems so straightforward when you think about it casually. We imagine it like a ruler, or a highway stretching endlessly in both directions, something you can measure, something that just keeps going at the same steady pace everywhere. But the deeper you look into how time actually works, the more you realize this simple picture breaks apart completely. The universe operates on rules that feel foreign to our everyday experience. Two people can witness the exact same event, and they might completely disagree about when it happened. One person says it occurred first, the other says it happened second. Both of them are absolutely correct. This isn't some philosophical debate about perception. This is built into the fundamental structure of reality itself. Einstein figured this out in the early 1900s, and what he discovered changed everything. Space and time, which everyone assumed were totally separate things, are actually woven together into a single fabric. Scientists call it space-time. When you stretch space, you automatically stretch time. When you bend one, the other bends right along with it. They're inseparable. This connection means time behaves nothing like we intuitively expect. Time isn't some unchanging backdrop that events play out against. It's dynamic. It responds to what's happening around it. Speed changes time. Gravity changes time. Both of them cause time to curve in ways that would sound impossible if we hadn't measured them directly. The simplest version of this is what happens when things move really fast, get close to the speed of light, and time slows down for you compared to someone standing still. Your clock doesn't break, your entire experience of time literally changes. You age more slowly. Your thoughts process differently. Every second stretches out. Particle accelerators prove this constantly. Unstable particles that should decay quickly end up lasting much longer when they're moving at high speeds. They don't somehow know they're moving fast. Their internal clocks are just ticking at a different rate. Time itself has been stretched for them. Even astronauts experience this effect. Someone spending months on the International Space Station, orbiting Earth at tremendous speed, ages slightly less than people on the ground. The difference is incredibly small. Just fractions of a second, but it's real and measurable. Speed genuinely affects the flow of time, but gravity does something even stranger to time. Picture space-time as a massive sheet stretched tight in every direction. When you place something heavy on that sheet, like a planet or a star, it sinks down and creates a depression. That curved dip changes how everything nearby moves through space. This is what gravity actually is. Not some invisible force pulling things together, but the shape of space-time itself. Planets orbit stars because they're following the straightest possible paths through this curved fabric. Those paths look like orbits to us, because the space they're moving through isn't flat anymore. Here's the remarkable part though. That curvature doesn't just affect space, it warps time too. The deeper you go into a gravitational well, the slower time runs. Stand on top of a mountain, and time moves slightly faster for you than someone at sea level. The effect is tiny, but atomic clocks can detect it easily. In stronger gravitational fields, this time dilation becomes much more dramatic. Near a black hole, space-time curves so severely that time practically grinds to a halt at the event horizon. From far away, anything falling toward a black hole appears frozen at that boundary, not because it actually stops moving, but because the light carrying information about its motion gets stretched out over longer and longer time periods. These curves in time aren't rare or exotic phenomena, they're everywhere around us. Your own body creates a tiny dent in space-time. So does your chair, your house, every object with any mass at all. The dents are incredibly small, but they're real parts of the universe's structure. Every curve changes the local experience of time, even if just by the tiniest amount. This is what makes relativity so different from how we naturally think about time. There's no universal clock ticking away at the same rate everywhere. Time is a flexible dimension that gets shaped by everything around it. Stack different effects together, motion and mass, acceleration and gravity, and you get even more complex patterns of time flow. Think about it like looking at a map. On a flat map, every inch represents the same distance, but on a globe, distances curve. The shortest path between two cities isn't a straight line on the flat map. It's an arc across the curved surface. Time works exactly the same way in curved space-time. The path between two events might not be what you'd expect. It depends entirely on the geometry of the space you're moving through. That geometry isn't even fixed. It changes as mass moves around, as energy flows from place to place. The shape of space-time evolves constantly, which means time evolves right along with it. This becomes especially important when you think about the very early universe. Right after the Big Bang, everything was compressed into an incredibly hot, dense state. The curvature of space-time was extreme beyond imagination. Time behaved completely differently then, not just faster or slower, but following entirely different rules. As the universe expanded, the geometry gradually changed, and so did the nature of time itself. Understanding the early universe becomes incredibly difficult because of this. You can't just rewind the clock, like a movie playing backward. You have to account for the fact that the clock itself was changing, not just what time it showed, but how time fundamentally worked. The same principle applies to the far future. As the universe continues expanding, possibly even accelerating, space-time stretches thinner. Galaxies drift farther apart, the curves of gravity flatten out. This has profound implications for how time flows. Far from any massive objects, in the deep future, time may behave differently once again. When scientists say time is curved, they're not speaking metaphorically. They're describing the actual behavior of time in the presence of mass and motion. They're explaining why clocks in different places don't always agree, why the concept of simultaneity breaks down completely, why the answer to what time is it depends entirely on where you're asking the question from. This raises some fascinating questions about extreme situations. What happens when the curves of space-time become so sharp that our mathematical models break down completely? Places like black hole singularities, or the very first moments of the Big Bang, where curvature becomes so intense that time might stop altogether or cease to have any meaning we could understand. But even before exploring those extreme edges, it's worth remembering that curved time isn't just something that happens in distant cosmic phenomena. Every clock you've ever looked at, on walls, on wrists, in phones, is following its own unique path through curved space-time. Your body, your thoughts, your entire experience of existence, all shaped by where you are, how you're moving, what massive objects are nearby. This isn't poetry, it's physics. You don't just live in time, you actually help shape it, simply by existing in the fabric of space-time. Relativity makes it clear that curved time is the only kind of time there actually is. The straight, uniform time we imagine is just an approximation that works when curves are too gentle to notice. So when we ask whether the universe knows what time it is, we have to be incredibly precise about what we mean. Where in the universe are we asking about? For whom? Under what conditions of motion and gravity? Because there's no single, universal answer. There's only time shaped by whatever curves it happens to be traveling through at any given moment. We track the passage of time through countless methods scattered across the natural world. Personal memories fade and shift, but they leave traces. Written records stretch back thousands of years, preserving fragments of human experience. Ice cores tell stories, locked in frozen layers, each one a snapshot of ancient atmospheres. Fossil layers stack like pages in an enormous book, written in stone and sediment. The motion of planets follows patterns we can trace backward, their orbits marking cosmic clockwork. Radioactive atoms decay at predictable rates, their breakdown serving as natural timekeepers. Each method takes us deeper into the past, but the signals grow weaker as we travel further back. The record becomes thinner, more fragmented, harder to read. Still, the timeline holds together. Physics gives us the tools to keep rewinding, to push further into yesterday than any single method could manage alone. Push far enough back, and something interesting happens. You're no longer just studying ancient events, cataloging what happened when. You're approaching something much more fundamental, the limits of time itself. This isn't because we run out of data to examine, though that happens too. It's because we encounter a deeper puzzle, one that challenges the very idea of before and after. The question becomes whether time had a beginning at all. That concept feels wrong somehow, unnatural. Everything we know seems to have a before attached to it. Trees fall, but there was a moment before they hit the ground. Stars explode, but there was a time when they burned quietly. Before the explosion began, our entire experience teaches us to expect a before for every event we encounter. But what about time itself? If time began at some point, what existed before that beginning? The answer might be that the question breaks down completely. Our minds work through cause and effect, through sequences, through the steady forward march of moments. We use that structure to think about everything else. When you ask what came before time, though, you're trying to use a time-based concept, the word before, to discuss a situation where time might not have existed yet. It's like asking what direction lies north of the North Pole. The words make sense individually, but the concept collapses when you examine it closely. You can say the phrase, but it doesn't point to anything real. According to our current best models, the universe has a measurable age. Around 13.8 billion years, give or take. That number isn't a guess or an estimate pulled from thin air. It comes from multiple independent lines of observation, all pointing toward the same conclusion. Galaxies are expanding away from each other at measurable rates. The cosmic microwave background radiation has cooled in predictable ways. Light elements exist in specific ratios throughout the universe. All these observations point back to a moment when everything we see was compressed into a much hotter, much denser, much simpler state. We call that moment the Big Bang, but the name creates some confusion about what actually happened. The Big Bang wasn't an explosion in space, not a burst that happened at a specific point and spread outward into empty surroundings. It was the rapid expansion of space itself. Space didn't expand into something else, because there was no something else to expand into. There was no center point, no outside boundary, no empty void waiting to be filled. Every point in the universe today was once part of that compressed, superheated state. When expansion began, it began everywhere at once. If you could somehow run that expansion backward, like rewinding a film, the mathematics would take you to a point of infinite density and infinite temperature, a singularity. But that singularity probably isn't a real physical place. It's more likely a breakdown in our equations, a spot where our current models stop being useful. Most physicists believe the singularity represents the edge of where general relativity applies, not an actual, infinite point in space and time. Beyond that edge, we would need quantum gravity, a theory that combines our understanding of very large-scale physics with very small-scale physics. The problem is, we don't have a complete theory of quantum gravity yet. Several candidates exist, but none are fully confirmed, even without quantum gravity. Though general relativity gives us something important. A starting line, a boundary, a lowest point on the cosmic timeline, not a place in space, but a moment in time. According to our current picture, time itself began with the Big Bang. There was no before, in the sense we usually understand a word, because time as a dimension, as a physical property of the universe, didn't exist yet. That idea creates a kind of mental glitch when we try to grasp it. We want to ask what caused the Big Bang, or what came before it. But if time began there, then causality, the whole concept of one thing leading to another, breaks down completely. The chain of events doesn't extend any further backward, not because something is hidden from us, but because backward stops being a meaningful direction. This breakdown has led to different theoretical approaches. Some suggest that time, like space, might be curved. In this view, the beginning of the universe resembles the South Pole more than a sharp edge. A smooth boundary, finite but without a clear starting point. Time might not have a beginning moment, so much as a rounded start, a finite past without a specific before. Other theories propose that time is emergent, that it arises from something more fundamental. Before the Big Bang, time as we experience it didn't exist, but some other process did. Time becomes a result, not a foundation. It emerges from the behavior of quantum fields, or from informational structures that operate according to different rules. If that's true, asking what happened before time is like asking what exists south of a flat drawing. The question simply doesn't apply to the situation. Some cosmological models include what's called a bounce. A previous universe collapsed down to a minimum size, then rebounded into the expansion we observe today. Our universe becomes one phase in a much longer cycle. Time didn't begin with our Big Bang, it just turned a corner, changed direction from contraction to expansion. These bounce models come in different varieties. Some suggest the bounce was smooth, like a compressed spring releasing its stored energy. Others involve quantum processes, where the collapse reached some critical threshold, then tunneled into a new expansion phase. A kind of cosmic reboot. In bounce scenarios, there is a before, but it might look nothing like what we recognize as a universe. No stars, no galaxies, possibly no dimensions like the ones we know. Time might not have flowed in a direction we'd understand, or the previous phase might not have been before at all, but rather a different part of the same larger structure. Testing these ideas directly is extremely difficult. Right now, we can't observe anything that happened before the cosmic microwave background formed. That radiation represents the afterglow of the early universe, light that's been stretched and cooled by billions of years of expansion. It still carries information about conditions a few 100,000 years after the Big Bang. Earlier than that, the universe was opaque, too hot and dense for light to travel freely. We can model those earlier phases using known physics, but as we push closer to the Big Bang itself, our equations lose confidence. We're working near, or possibly beyond, the edge of what general relativity can reliably describe. Quantum gravity theories all seem to agree that time at the most fundamental level behaves very differently than what we experience day to day. It might not be continuous, flowing smoothly from one moment to the next. It might not be directional, always moving from past toward future. It might not even be fundamental, but instead statistical probabilistic, derived from something deeper and stranger. If that's correct, then our everyday notion of a timeline, a sequence of moments stretching from past to future, is just a useful approximation. A large-scale behavior that emerges once the universe develops enough structure to support it. Asking where time begins becomes less about pinpointing a specific moment, and more about identifying a threshold, the point where conditions allowed time to exist in a form we'd recognize. Before that threshold, something else was happening. We just can't define what that something else might have been, using the concepts and language available to us now. Even if time does have a beginning, that beginning might not work the way we expect beginnings to work. It might not have had a cause, might not have happened at a specific location, might not have started from a state of rest. It might simply be a property that emerged when certain relationships took shape in the early universe. In physics, many properties work this way. Temperature and pressure don't exist without systems of moving, interacting molecules. Maybe time is similar. Maybe the early universe didn't start in time, but rather started into time, creating the conditions that allow temporal experience to exist. This perspective makes the original question more precise. Instead of asking what was before time, we start asking what conditions allow time to emerge. What do we mean by a beginning, when there's no pre-existing time to measure it against? How do we think about causation without the framework of sequential moments? These questions point us toward the edge of what we can currently know. Not an ending, not an impassable wall, but a frontier. A place where our maps fade and the possibilities multiply. We might never discover what, if anything, came before time as we understand it. But the search itself teaches us something valuable with every step, not just about the universe's history, but about the nature of time itself. Time isn't just a series of moments ticking by, isn't just a background against which events unfold. It's a structure that responds to motion, to mass, to entropy, to the very act of making observations. We live inside that structure, shaped by it, moving through it. Whether time began at a specific moment or emerged gradually from something else entirely, it brought us to this point. This moment of wondering, of pushing against the boundaries of what minds like ours can grasp. And maybe that's the most remarkable thing about time, not where it came from, but where it's taken us. Time passes differently when you think about it in cosmic terms. Most seconds slip by without us noticing them at all. But there was one second that changed everything, the very first one in our universe's existence. That moment wasn't quiet or gentle. It was explosive, chaotic, and completely packed with energy. When we try to imagine the beginning of everything, we have to forget what we know about normal time. The universe didn't start as a tiny dot sitting in empty space. It was space itself, compressed into something we can barely comprehend. Temperature and density reached levels that would make the core of our sun seem cold by comparison. Physics itself was still figuring out its own rules. Something triggered an expansion, though we still don't know what. The moment that expansion began, time became real. Events could happen in sequence. Cause and effect started working. And almost immediately, something extraordinary occurred. A process scientists call inflation. This wasn't just the universe getting bigger. It was space itself stretching at an incredible rate. In less than a trillionth of a second, the universe grew by an enormous amount. It expanded faster than light, which sounds impossible until you realize it wasn't matter moving through space. Space itself was expanding. No speed limits were broken, but distances between points grew at a rate that defies our everyday understanding. This inflation period explains something puzzling about our universe today. When we look in opposite directions, we see regions that appear very similar, even though they're so far apart that light hasn't had time to travel between them since the beginning. Inflation solved this by stretching a small, uniform region into the vast cosmos we observe now. Then inflation stopped, just as suddenly as it began. That transition released massive amounts of energy, reheating everything and filling space with particles and radiation. This marks what we call the hot Big Bang phase, where our more familiar physics starts to apply. The clock keeps ticking, but each microsecond matters enormously. Within the first 100,000th of a second, the universe becomes a sea of fundamental particles. Quarks, gluons, electrons, neutrinos, and photons are constantly colliding, forming temporary structures that immediately break apart again. No atoms exist yet, no protons or neutrons, just an incredibly hot plasma soup. During this time, the four fundamental forces begin to separate from each other. Gravity becomes distinct first, then the strong nuclear forces emerges, followed by the electromagnetic and weak nuclear forces splitting apart. These aren't just academic divisions. They determine what kinds of particles can form, which ones can decay, and what reactions become possible. As expansion continues, cooling follows, and cooling changes everything. Around 1 microsecond after the beginning, quarks start combining into protons and neutrons. The temperature is still over 1 trillion degrees, but the universe now has structure. It has matter instead of just raw energy. By the end of the first millisecond, the basic building blocks of atomic nuclei are in place. The atoms themselves won't form for much longer, but their components are here. During this phase, something interesting happens with neutrinos. These ghostly particles stop interacting with matter and begin moving freely through space. Some of the neutrinos created in that first second are still traveling through the universe today, passing through your body right now, without you feeling anything. Around this time, one of the most important events in cosmic history occurs: the disappearance of antimatter. Initially, the universe contained equal amounts of matter and antimatter. When these particles meet, they annihilate each other, converting into pure energy. For every billion pairs that cancelled out, just one extra particle of matter remained. That tiny imbalance, just one part in a billion, is why anything exists today. We still don't understand why this asymmetry occurred. The laws of physics seem to treat matter and antimatter equally, yet something broke that symmetry in the early universe. That slight preference for matter over antimatter is the reason stars, planets, and people can exist. It's one of the deepest unsolved mysteries in physics. By the time a full second has passed since the beginning, the universe has cooled to about 10 billion degrees. That's still hotter than any star's core, but it's cool enough for nuclear reactions to begin. Neutrons and protons start binding together, forming the first atomic nuclei, mostly hydrogen and helium, with tiny amounts of lithium. The electrons are still moving freely at this point, so the universe remains a plasma, where light can't travel far without scattering off particles. It will take hundreds of thousands of years before neutral atoms form and the universe becomes transparent to light. But that first second has already accomplished something remarkable. All the matter that will eventually form galaxies, stars, and planets is already present. The physical laws governing energy and motion are established. The temperature has dropped from near infinity to levels where chemistry and complex structures will eventually become possible. What's fascinating is how that initial moment set up a clear direction for everything that followed. The universe moves from higher energy states to lower ones, from perfect symmetry to increasing complexity, from smooth uniformity to rich structure. Every process afterward follows these patterns established in that first second. Everything that comes later is essentially elaboration on themes introduced in that opening moment. Galaxies won't form for hundreds of millions of years. Stars take even longer, but these are slow, predictable processes governed by gravity, gradually pulling matter together. The first second was different, fast and wild, packed with transformations that happened once and never repeated. We can't observe that first second directly, but we can infer what happened through multiple lines of evidence. The cosmic background radiation carries information from when the universe first became transparent. Particle physics experiments recreate similar energy conditions in accelerators. The distribution patterns of galaxies trace back to tiny density variations from the earliest moments. All this evidence points to a universe that was once incredibly small, hot, dense, and changing rapidly. Computer simulations help us understand the particle interactions. Laboratory experiments test our theories about early universe conditions. Astronomical observations reveal the consequences of those initial moments. The first second didn't contain everything that would ever exist, but it contained enough. Enough for time to have meaning, enough for matter to survive the cosmic violence, enough for gravity to begin its patient work of building structure. Once that moment passed, it was gone forever. The universe expanded, cooled, aged, and became what we see today. Yet that first second remains with us in subtle ways. The ratios of hydrogen and helium we observe, the neutrinos still streaming through space, the matter-antimatter imbalance. All these are echoes from that primordial time. They haven't changed despite billions of years of cosmic evolution. We live in the aftermath of that incredible moment. Our models and theories exist in its shadow. Scientists keep working to understand how so much transformation could happen in such a brief time. It's a reminder that the most important changes sometimes occur in the smallest intervals. This raises profound questions about the nature of time itself. If the universe had such a dramatic beginning, compressed into a single second of unimaginable activity, what does that tell us about endings? Does the universe have a final moment waiting somewhere in the distant future? And if so, will it be as sudden and transformative as its beginning was? The universe has a curious habit that might keep you up at night, thinking about it. Every morning you wake up, remembering yesterday, not tomorrow. Your coffee gets cold, never hot. Your phone battery drains, never charges itself. This isn't just how things happen to work. It's the fundamental rhythm of everything that exists. Scientists call this rhythm the arrow of time. And here's what's strange about it. The basic laws that govern reality, Newton's equations, electromagnetic fields, even the weird rules of quantum mechanics, they don't actually care which direction time moves. You could run the math backwards and get perfectly valid results. The equations work both ways, but reality doesn't work both ways. Eggs break, they don't unbreak. People age, they don't get younger. Rivers flow downhill, not up. So there's this puzzling gap between what the equations allow and what actually happens in the world around us. The answer lies in something called entropy. Think of entropy as nature's way of keeping score of how messy things get. When you have a deck of cards in perfect order, that's low entropy. Shuffle them randomly, that's high entropy. The key insight is this: there are millions of ways to shuffle a deck randomly, but only one way to put it in perfect order. So when things get disturbed, they almost always end up messier than they started. Not because some force pushes them that way, simply because messy outcomes vastly outnumber neat ones. It's pure statistics. This is why time seems to flow forward. The air molecules in your room could theoretically all suddenly rush to one corner. The physics doesn't forbid it, but the probability is so impossibly small, you could wait longer than the age of the universe and never see it happen. Every natural process increases the total amount of disorder in the universe. That's the second law of thermodynamics, and it's what creates the arrow of time. Your memories work in one direction because the information gets encoded as entropy increases. Your body ages because biological processes create more disorder even as they maintain the order of your cells. But this creates a deeper mystery. If entropy is always increasing now, it must have been much lower in the past. Wind back the clock far enough, and the universe started in an incredibly ordered state. Dense, smooth, uniform. Almost no entropy at all. Why did the universe begin so tidy? Nobody knows for sure. You could imagine a universe that started chaotic, with maximum entropy from day one. But that universe wouldn't have an arrow of time. Nothing would change. Nothing would develop. Everything would already be at equilibrium. Instead, our universe started far from equilibrium. This gave it somewhere to go, something to become. As it expanded and cooled, structure began forming. Galaxies, stars, planets, eventually life. Paradoxically, these organized structures exist because the total entropy keeps increasing. The universe becomes more complex locally, even as it becomes more disordered globally. Think about a star burning in space. It's converting hydrogen into helium, creating heat and light, increasing entropy. But that same process makes planets possible, and chemistry and biology. Order and disorder dance together, with disorder always winning in the end, but order getting more interesting along the way. This raises fascinating questions about different corners of the universe. Does the arrow of time point the same direction everywhere? Near black holes, space and time get twisted into bizarre shapes. Information seems to disappear, though physicists suspect it's actually preserved in ways we don't understand yet. The arrow might still exist there, but warped beyond recognition. In the quantum world, things get even stranger. Some interpretations suggest that time doesn't really flow at all. Instead, all possible futures exist simultaneously until something forces a choice. When you observe a quantum system, you're not seeing what was always there. You're participating in selecting which possibility becomes real. This connects the arrow of time to information itself. You remember the past because information about it exists, encoded in your brain, in the arrangement of atoms around you, in the traces left by events. The future hasn't happened yet, so no information about it exists anywhere. Every moment creates records. Every interaction leaves marks. And these marks only point one way. You leave footprints after you walk, not before. Photographers capture what already happened, never what's about to happen. The universe is constantly writing its own history, but never its future. Could the arrow ever reverse? Probably not, even in the most extreme scenarios. Some cosmological models predict the universe might eventually stop expanding and collapse back on itself. But most physicists think entropy would keep increasing even during such a contraction. The arrow would still point forward, toward greater disorder. If expansion continues forever, we're heading toward what's called heat death, not a fiery destruction, but a quiet end. All the stars will burn out. All the black holes will evaporate. Matter itself will decay. The universe will become a uniform, changeless fog of particles at the same temperature. Maximum entropy, no more structure, no more change, no more arrow of time, not because time stops, but because there's nothing left to change. It would be like a perfectly shuffled deck of cards that stays perfectly shuffled forever, but that's trillions of years in the future. Right now, entropy is still climbing, stars are still burning, brains are still thinking, the arrow still points forward, and we're riding along with it. Your entire existence happens in the context of this cosmic settling process. Every breath you take, every thought you think, every decision you make occurs as the universe continues its long journey from the pristine order of its birth toward the deep randomness of its distant future. The arrow of time isn't built into the fabric of space itself. It's built into the process of change, into heat, flowing from hot to cold, into complex systems forming and dissolving, into information accumulating and memories forming. We live in a universe that's still young enough to be interesting, still far enough from equilibrium to allow for complexity, structure, life, consciousness. The arrow points forward because there's still somewhere to go, still room for the cosmic story to unfold. And we're part of that unfolding, temporary arrangements of matter and energy, riding the arrow from order toward chaos, leaving our own small traces in the vast process of change. The universe operates under rules we can't hear, silent principles that shape everything without fanfare. There's this fundamental concept in physics called entropy, and it works quietly in the background of every moment. Think of it as nature's accounting system, always keeping track of how energy gets spread around. When the universe first began, everything was incredibly smooth and uniform. All that energy was packed together in this neat, organized state. But from that moment forward, entropy started its slow, steady climb upward. It's been increasing ever since, not dramatically, but consistently, like water finding its way downhill. Here's the fascinating thing about probability and disorder. When you drop cream into your morning coffee, it swirls around and mixes completely. You never see it spontaneously separate back into pure coffee and pure cream. That's not because the laws of physics forbid it. It's because the mixed state represents so many more possible arrangements of those molecules. The mathematics of probability heavily favors the mixed outcome. This same principle applies everywhere in nature. Gas molecules in a closed room will spread out evenly, never clustering back into one corner on their own. Heat flows from warm objects to cool ones, not the reverse. Stars radiate energy outward into space, and that energy doesn't magically collect itself back together. Once energy disperses, it stays dispersed. The second law of thermodynamics captures this reality perfectly. It states that entropy always increases in isolated systems. This law gives time its arrow, its sense of forward direction. We remember the past and anticipate the future because entropy was lower yesterday than it is today, and it will be higher tomorrow than it is now. But this steady increase in entropy points towards something profound about the universe's ultimate destiny. If disorder keeps growing, there must be a limit, a final state where no more useful energy remains. Scientists call this theoretical endpoint the heat death of the universe. Don't picture heat death as some fiery catastrophe though. It's more like a gentle evening out, a gradual leveling of all energy differences. Right now, the universe buzzes with activity. Stars burn bright, black holes devour matter, planets cool slowly in the void. All of this represents useful energy doing work, creating temperature differences, driving motion and change. But every time energy moves from a hot place to a cold place, entropy increases slightly. That cooling cup of tea on your table, that star radiating into empty space, they're all part of this same universal pattern. Energy flows outward, always seeking balance, never returning to its concentrated state without outside help. Over unimaginably long periods, far exceeding the current age of the universe, stars will exhaust their nuclear fuel. Some will explode as supernovas, others will collapse into dense remnants. White dwarf stars, neutron stars, and black holes will mark the graves of stellar systems. The bright era we're living through now represents just a brief chapter in cosmic history. Even after the last star fades, the story continues. Those stellar remnants will persist, slowly cooling as they radiate away their remaining heat. The expansion of space itself plays a crucial role here. As the universe stretches, energy gets diluted across ever larger volumes. The background temperature drops steadily toward absolute zero. Eventually, only black holes will remain as significant structures in the cosmos. You might think these represent permanent features, but even black holes have expiration dates. Stephen Hawking discovered that black holes emit radiation, a quantum mechanical process that causes them to gradually evaporate. Massive black holes take longer to disappear than small ones, but given enough time, every single one will vanish completely. After the last black hole evaporates, the universe will contain nothing but a thin, cold soup of elementary particles. No stars, no planets, no structures of any kind. Maximum entropy will have been reached. This represents true heat death. Not because everything is hot, but because no temperature differences remain to drive any processes. This might sound like the end of time itself, but time continues flowing. It's just that nothing interesting happens anymore. No energy flows, no particles interact meaningfully, no information gets processed. The universe reaches a state of perfect thermodynamic equilibrium. This transition won't happen suddenly. We're talking about a timescale that dwarfs human comprehension. Trillions upon trillions of years, stretching into an almost infinite future. The heat death represents a slow fade rather than an abrupt conclusion. Some people find this vision of the future deeply unsettling. It suggests that everything we do, everything we build, every civilization that rises, ultimately amounts to nothing in the cosmic scheme. But there's another way to look at it. This isn't failure, it's completion. The universe started far from equilibrium and gradually explores all possible configurations on its way to the most probable final state. Entropy doesn't just drive things toward disorder, it enables complexity along the way. Your own body represents a perfect example of this principle. You're constantly increasing the entropy of your environment through breathing, digestion, and metabolism. You consume low-entropy food and convert it into motion, thought, and waste heat. You're a temporary pocket of order in a universe trending toward disorder. This is completely allowed by thermodynamics because your local decrease in entropy comes at the cost of a greater increase in entropy elsewhere. The net result still moves in the direction of higher overall entropy. You're not fighting against the second law, you're participating in it. The same principle applies to all complex structures in the universe. When a star forms from a collapsing gas cloud, it creates local order through nuclear fusion, but it radiates far more energy into space than it organizes internally. Galaxies, planets, ecosystems, all of these represent temporary organizations that accelerate the overall increase in entropy. Life itself can be understood as an entropy increasing process. Living systems are remarkably efficient at capturing energy and dispersing it as waste heat. In a strange way, biological complexity exists, not despite entropy, but because of it. We're nature's way of speeding up the journey toward thermodynamic equilibrium. This perspective makes the eventual heat death feel less like a cosmic tragedy and more like a natural conclusion. The universe is telling a very long story, one that includes every star that ever shone, every planet that ever formed, every thought that ever occurred. We're chapters in this story, not the final word. Memory itself represents a form of entropy increase. Every time you remember something, You're creating a physical trace in your brain, a change that requires energy and increases disorder somewhere else in the system. Information has thermodynamic costs, and recording experiences always comes with an entropy price tag. Right now, we're nowhere near the heat death scenario. The universe remains young and energetic, full of possibilities for structure formation and complex processes. Stars continue forming in stellar nurseries, galaxies collide and merge, planets develop and evolve. The entropy slope may lead toward flatness eventually, but it's still steep enough for countless interesting things to happen. The arrow of time remains sharp and well-defined. Clocks tick forward, causes precede effects, and the future holds genuine surprises. We have billions of years before our own sun exhausts its fuel, and trillions more before the last stars fade. That provides ample time for whatever developments await, whatever forms of complexity might emerge. Entropy operates like a patient accountant, tallying up each energy transaction without rush or urgency. Every process that occurs, from stellar fusion to human consciousness, contributes to this cosmic bookkeeping. The total always increases, but the path from here to maximum entropy winds through territories we can barely imagine. The gentle fade awaiting the universe represents not an ending, but a completion, the final accounting of a process that began with the Big Bang. It's simultaneously humbling and magnificent. This recognition that we participate in something so much larger than ourselves, something that connects every moment to every other moment through the steady, inexorable climb of entropy toward its ultimate destination. Time reveals itself through motion, through the steady march of change that surrounds us every moment. Your heartbeat marks seconds, the sun traces its path across the sky, cells divide and age, thoughts form and dissolve. These processes don't just happen in time, they actually create our experience of what time means. The universe right now pulses with activity. Trillions of stars fuse hydrogen into helium in their cores. Galaxies spiral through space, occasionally colliding in cosmic dances that last millions of years. Particles zip around, decay into other particles, interact in ways we can measure and predict. Each of these events slices time into measurable chunks, giving us a rhythm, a beat we can follow. But this busy universe won't stay busy forever. Eventually, entropy will reach its maximum, a state physicists call heat death. It's not just that things get cold and quiet. It's that all the contrasts disappear. No more stars burning bright against dark space. No more planets orbiting in predictable paths. No more matter clumping together or falling apart in ways we can track. Here's where things get philosophically interesting. Modern physics suggests time isn't just a background stage where events play out. In Einstein's relativity, time gets tangled up with space itself, creating space-time, a structure that bends and warps based on mass and energy. Your clock doesn't tick the same way everywhere. It runs differently depending on how fast you're moving, how deep you are in a gravitational field. This means time emerges from the behavior of matter and energy, rather than existing independently. It's not a river flowing at a constant rate. It's more like a dance that matter and energy perform together, and the dance changes depending on the dancers. Quantum mechanics makes this even stranger. Some interpretations suggest time isn't fundamental at all. Instead, systems evolve relative to other systems. Time becomes a label we use when we compare changes in one thing to changes in another. This electron spin compared to that photon's path. This atom's vibration compared to that electromagnetic field. If nothing changes, if everything becomes perfectly static, then there's nothing to compare, no before and after, no tick of progression. You could still define time mathematically, write equations that include it, but physically it would become meaningless. Imagine a room where absolutely nothing moves, no particles drift, no atoms vibrate, no light travels, no heat flows. The temperature stays perfectly uniform everywhere. In this frozen state, you could claim time is passing, but what evidence would support that claim? From whose perspective would you measure it? This matters when we think about the far future. As entropy increases, usable energy decreases, and processes slow down dramatically. First, the stars burn out. Then comes the slow, gravitational collapse of remaining matter. Black holes form, and then evaporate over time spans so vast they defy comprehension. After all that, what remains? A thin, uniform spread of extremely low-energy particles, mostly photons, some neutrinos, possibly dark matter, all spreading apart forever in an expanding space. If nothing interacts anymore, if no new structures can form, if no patterns emerge from the uniformity, then there's nothing left to tell time by. The timeline still exists. You could still label coordinates on it. But there's no motion, no sequence, no natural clocks ticking away moments. Time loses its meaning, like having a measuring stick in a universe with no distances left to measure. The tool exists, but there's nothing to use it on. This is what physicists mean when they talk about time ending. Not that it disappears like a snapped rope, but that it fades into irrelevance. It becomes invisible, not false exactly, but empty of content. The concept of a ticker becomes crucial here. A ticker is any process that can count, that can mark intervals. A pendulum swinging, an atom vibrating at a specific frequency, a radioactive nucleus decaying, a gas cloud collapsing under its own gravity. We compare change against change, rhythm against rhythm. Remove all the tickers and time doesn't stop existing, but it stops being something anyone could experience. This represents the deepest version of heat death, not just cold and still, but undifferentiated. A system where literally nothing happens, where time exists only as an abstract coordinate with no physical meaning. Does this make time subjective? Not entirely. It still exists in our equations. The universe still has a history. Space-time still has structure. But your experience of time, your sense of now, of duration, of sequence, that depends completely on having processes to observe. Without them, time becomes like a color in a world without light. This isn't destruction in any dramatic sense. It's dilution. Everything that once marked time's passage spreads out so far, becomes so perfectly even, that it leaves no differences behind. You can't track changes that never vary from one moment to the next. The question remains whether time would still be real in such a universe. Some physicists say yes. It exists regardless of observation. Others argue it becomes meaningless without processes to define it. Still, others suggest the question itself doesn't matter, because a universe without change has no observers, no processes, no outcomes that could care about the answer. But we're not in that universe yet. We're surrounded by tickers right now. Earth spins on its axis. The moon tugs at our oceans. Stars shine across vast distances. Galaxies drift through expanding space. Even in your body, neurons fire, blood flows, chemical reactions proceed at measurable rates. Motion and relationships surround us, which means time surrounds us too. This lets us ask what time would mean without clocks. What happens when all the natural timekeepers finally wind down? When decay processes end? When energy reaches its lowest possible levels? When the universe settles into a state so uniform that no part differs from any other part? What you're left with is a structure that no longer carries rhythm. No cycles, no pulses, no changes in state. Just one long, flat drift through coordinates that no longer register differences. Time without tickers isn't gone, but it becomes unreachable, unobservable, practically meaningless. That may represent time's final phase. Not a wall or a sudden stop, but a flat line stretching endlessly with nothing left to count. Nothing left to mark the passage of moments that no longer feel like moments at all. At the very smallest scales of existence, time takes on qualities that challenge everything we think we know about reality. When we peer into the quantum realm, we discovered that particles don't behave like the objects we encounter in daily life. Instead of following clear, predictable paths, they exist in what scientists call superposition, a strange state where multiple possibilities coexist simultaneously. Picture a coin spinning in the air, neither heads nor tails, but somehow both until it lands. Quantum particles exist in a similar limbo, spread across clouds of probability, rather than occupying definite positions. These probability clouds shift and evolve, but not in the straightforward way we might expect. They don't move from point A to point B like a car traveling down a road. This creates a fascinating puzzle about the nature of time itself. In our everyday world, we can always ask where something is and how fast it's moving. We can trace clear trajectories and assign specific times to every moment along the way. But quantum mechanics operates by entirely different rules. When we can't pinpoint exactly where a particle is or predict exactly what it will do, how do we even begin to talk about time? The mathematical framework that governs quantum behavior treats time as what physicists call a parameter. Think of it as a dial you can turn to see how the system changes. But here's the peculiar thing. The equations don't actually explain what time is. They simply assume time exists and use it to describe how probabilities evolve. It's like having a recipe that tells you to bake for 30 minutes without ever defining what minutes actually are. Consider how we measure time in our daily lives. We rely on clocks, devices that count regular intervals, whether it's the swing of a pendulum or the vibration of a quartz crystal. Scientists have developed incredibly precise atomic clocks that measure the frequency of electromagnetic radiation as atoms jump between energy states. These devices can track time with extraordinary accuracy, but as we zoom deeper into the quantum world, the very concept of a clock becomes problematic. A quantum system in superposition doesn't tick in any conventional sense. It exists in multiple states simultaneously, only collapsing into a definite result when it interacts with something else, when it gets measured. Before that moment of measurement, it doesn't follow a timeline. It simply floats in a sea of possibilities. This leads to one of the most profound questions in modern physics. If the fundamental building blocks of reality don't follow clear timelines, what does that tell us about time itself? Some researchers propose that time isn't actually a basic feature of the universe. Instead, it might be what we call emergent, arising only when many quantum systems interact together. Temperature provides a useful analogy here. A single molecule doesn't have temperature in any meaningful sense. Temperature only becomes relevant when you have countless molecules moving around, creating patterns that we can measure statistically. Perhaps time works similarly, becoming apparent only when enough particles get involved in the cosmic dance. Some theories push this idea even further, suggesting that the universe might be fundamentally timeless at its core. In this view, the deepest laws of nature don't describe change at all. They describe relationships between different aspects of reality. What we experience as time might simply emerge from comparing these relationships, like reading the positions of clock hands relative to each other. This concept, known as the problem of time in quantum gravity, represents one of the biggest unsolved mysteries in theoretical physics. When scientists try to merge quantum mechanics with Einstein's general relativity, when they attempt to build a unified theory of everything, time becomes a major obstacle. The usual understanding of time doesn't appear naturally in many of the proposed equations. Researchers have to artificially insert it back through approximations and assumptions. This creates an even stranger puzzle. If time doesn't exist at the fundamental level, why do we experience it so consistently? Why does it feel so real and universal? One possible answer involves the quantum phenomenon of entanglement, where particles become correlated in ways that transcend ordinary space and time. When quantum systems interact with their environments, their possible states collapse into definite outcomes through a process called decoherence. Each interaction essentially writes a small piece of history, creating a record of what happened. As these records accumulate in complex systems, they might pile up into something resembling a timeline. Maybe time isn't real at the deepest level of reality. Perhaps it's more like a bookkeeping system, a convenient way to describe patterns in how probabilities change as systems become more complex. This doesn't diminish its importance in our lives, but it suggests that our intuitive understanding of time might be incomplete. Even if time isn't fundamental, quantum systems still exhibit dynamics. They still change and evolve. The mathematical descriptions of these systems, like the famous wave function, continue to evolve over time. In some sense, these changes represent the tiniest ticks of the cosmic clock, but these aren't the smooth, regular ticks of a mechanical timepiece. They jitter and flick unpredictably. They jump discontinuously when measured. The path from one quantum state to another isn't a smooth curve, but rather a probability cloud that suddenly becomes definite through measurement. This quantum jitter isn't just noise or imperfection in our measurements. It represents the actual texture of reality at the smallest scales. In quantum field theory, even completely empty space buzzes with activity. Fields vibrate constantly, particles pop in and out of existence, creating what physicists call vacuum fluctuations. These fluctuations have real, measurable effects. They produce the Casimir effect, where metal plates in a vacuum experience a tiny attractive force. They contribute to the mysterious dark energy that's driving the universe's expansion. They remind us that even in apparent stillness, the quantum world never stops moving. If time has any meaning at these scales, it's intimately connected to these fluctuations. Perhaps the fundamental tick of time isn't the swing of a pendulum or the oscillation of a clock, but the constant flicker of probabilities adjusting themselves with every quantum interaction. You can observe this quantum randomness in radioactive decay. A single radioactive atom contains no internal clock, telling it when to decay. The process happens unpredictably, governed purely by probability. While we can predict the half-life of large groups of atoms with great precision, individual atoms decay according to quantum randomness. Quantum tunneling provides another example of this probabilistic behavior. Sometimes a particle facing an energy barrier will appear on the other side, even though it doesn't have enough energy to climb over. Classical physics would forbid this, but quantum mechanics allows for a probability that the particle will tunnel through. These quantum effects aren't just laboratory curiosities. They play crucial roles in everyday processes. Photosynthesis in plants relies on quantum coherence to transfer energy efficiently. Chemical reactions in our bodies use quantum tunneling. The electronic devices we depend on exploit quantum properties of materials. Throughout all these processes, the quantum jitter continues. This makes time fundamentally messy at small scales. You can't assign a universal now to a quantum system the way you can mark time on a calendar. You can't rewind a quantum measurement or predict exact outcomes, only probabilities. This isn't a limitation of our instruments or theories. It's a fundamental feature of how the universe operates. The uncertainty isn't something we'll eventually overcome with better technology. It's built into the fabric of reality itself. When we ask what time looks like in the quantum world, we're not looking for a cosmic stopwatch. We're examining a process that only becomes time-like when many possibilities collapse into definite outcomes. This collapse doesn't necessarily erase the other possibilities. In some interpretations of quantum mechanics, like the many worlds theory, those other outcomes continue to exist in parallel realities. In all interpretations, though, time only reveals itself at moments of interaction and measurement. It's not flowing continuously underneath quantum systems like a hidden river. It emerges precisely when possibilities become actualities, when the quantum dice finally show their faces. This forces us to reconsider what we mean by concepts like before and after. In the quantum realm, these temporal labels aren't automatic or universal. They depend on context, on what's being observed, on what counts as a measurement, and on what serves as a clock. Perhaps time at the quantum level resembles an ocean more than a river. It's smooth in some regions, turbulent in others, calm where no events occur, and bubbling with activity where interactions happen. These bubbles of activity, the quantum jitters, generate everything we observe in the larger world. When enough of these microscopic fluctuations align, when sufficient quantum systems interact, patterns emerge, clocks become possible. The familiar flow of time that we experience begins to take shape. But underneath this apparent order, time remains fundamentally jittery, discontinuous, and probabilistic. The implications extend far beyond abstract physics. Every moment of our lives, every thought in our minds, every beat of our hearts, emerges from countless quantum interactions. The smooth passage of time that feels so natural and inevitable actually builds itself up from an underlying foundation of uncertainty and probability. Yet despite all this randomness and ambiguity, quantum fluctuations somehow add up to create order. They accumulate into patterns, they power change, they drive the processes that make life and consciousness possible. They represent the smallest conceivable ticks of time's clock, so perhaps this is where time truly begins, not in the grand motions of planets and stars, not in the mechanical precision of human-made clocks, but in the quantum moment when possibility becomes reality. When the wave function collapses, when superposition gives way to definite outcomes, when potential transforms into history. It happens not with dramatic fanfare, but with the subtlest of flickers. And from these countless tiny flickers, separated by intervals almost too small to imagine, emerges the time we know, the time we live in, the time that carries us forward through the unfolding story of existence. Time doesn't need our permission to exist. Your brain creates its own version of time, completely separate from any clock on the wall. Even when you're fast asleep, dreaming of impossible things, time keeps flowing through your mind like water through a riverbed. The human brain operates more like a collection of different timepieces, each ticking at their own pace. There's no master clock sitting in your head counting seconds like a metronome. Instead, your sense of time emerges from the constant chatter between different brain regions, each one contributing its own rhythm to the symphony. Deep inside your brain sits a tiny cluster called the suprachiasmatic nucleus. About 20,000 neurons huddle together there, working as your body's approximate timekeeper. They don't know what time it actually is, but they maintain your circadian rhythm, that roughly 24-hour cycle that tells you when to sleep, when your body temperature should rise or fall, when hormones should flood your system. This little neural cluster adjusts itself based on light signals from your eyes. It's not precise to the second, but it's accurate enough to anchor your sense of day and night. Without it, you drift through time like a ship, without an anchor. But that's just one layer of your brain's timekeeping system. The cerebellum handles those lightning-fast intervals, fractions of seconds, that matter when you're catching a falling glass or stepping off a curb. The basal ganglia, those regions tied to movement and reward, measure out seconds and minutes. Your prefrontal cortex takes on the longer durations, managing attention and expectation across hours or days. These different brain regions don't always agree on what time feels like. They each maintain their own sense of rhythm, their own way of tracking change. When they interact, your perception of time becomes something fluid, something that bends and stretches depending on your circumstances. This explains why time feels so different, depending on what you're doing. Boredom stretches time like taffy, making minutes feel like hours. Deep focus compresses time, making hours vanish like minutes. During a crisis, your brain suddenly records everything in slow motion, creating those vivid, frame-by-frame memories of accidents or emergencies. Dreams offer the most fascinating window into how your brain constructs time. When you dream, your body lies still. Your senses receive almost no input from the outside world, yet your brain often becomes more active than when you're awake, especially during REM sleep when the most vivid dreams occur. During REM, activity surges in your visual cortex, your emotional centers, your motor regions. But activity drops dramatically in the dorsolateral prefrontal cortex, the part of your brain responsible for logical reasoning and critical awareness. This is why dreams feel completely real while you're experiencing them, even when they involve flying elephants or conversations with long-dead relatives. In this altered state, time continues to flow, but not always in realistic ways. Some dreams feel like they last for hours, but actually unfold in just a few minutes. Others seem brief but somehow contain years of experience. Your dreaming brain can maintain relatively accurate timing for certain tasks, but it can also bend, jump, and loop time in impossible ways. Researchers have studied this by working with lucid dreamers, people who become aware they're dreaming while still inside the dream, These dreamers can signal researchers with specific eye movements, allowing scientists to measure the intervals between dream events and real time. The results show that dream time sometimes maps fairly closely to real time, but often it doesn't. This reveals something profound about how your brain actually processes time. Your brain isn't counting seconds like a stopwatch. Instead, it constructs a timeline out of events, experiencing time through change and memory rather than measuring it mathematically. Memory plays the crucial role here. Your sense of time depends heavily on how many changes you can recall. If lots of events happen, time feels full and substantial. If few things happen, time feels thin and empty. This principle becomes even more pronounced in dreams, where you experience time without any external anchors, no clocks, no sun, no schedules, just the unfolding of imagined events. That those imagined events are enough to give time a recognizable shape. This tells us that time, as we experience it, isn't just about the external world. It emerges from internal rhythms, internal records, internal changes happening inside your mind. This explains why two people can experience the same moment so differently. One person feels rushed and anxious, counting every second. Another feels calm and unhurried, floating through the same span of time. The external clock reads the same for both, but their internal clocks are completely personal. This internal sense of time also changes as we age. Children experience time very differently than adults, partly because everything in their world is new. Novelty stretches time, makes it feel longer and fuller. A single day in a child's life can feel endless, because their brain is constantly recording new patterns, new memories, new experiences. As we get older, repetition sets in. We encounter fewer genuinely new experiences, fewer surprises. The brain starts compressing similar memories together, making days blend into each other, weeks vanish without trace. Time seems to accelerate, not because it actually moves faster, but because the brain leaves fewer distinct marks in memory. Dreams can sometimes reverse this effect. They restore novelty to experience, creating strange connections between unrelated memories, mixing familiar elements in unfamiliar ways. This is why dreams can feel surprisingly long, even when they're actually brief. They're dense, with activity, packed with difference and change. This elasticity of mental time serves as one of the brain's survival tools. You don't need perfect timekeeping to survive and thrive. You need useful timekeeping, accurate enough to coordinate with others, anticipate future events, and respond appropriately to changing circumstances. When your body rests, your mind doesn't simply stop working. It keeps exploring, sometimes replaying the day's events, sometimes inventing new scenarios, sometimes sorting through memories and experiences, but always, it maintains some form of rhythm, some sense of sequence and duration. Even when you're completely unaware, some part of your consciousness continues keeping time. This raises deeper questions about the nature of time itself. If time feels completely real even when it's constructed from dreams, guesses and fragmented memories, then what is time really? The clocks that physicists study depend on energy, on atomic decay, on systems in constant motion. But the clocks in your mind depend on attention, on emotion, on the density of memory and meaning. These two types of time aren't identical, but they mirror each other in fascinating ways. A radioactive isotope decays at a perfectly fixed rate, governed by the fundamental laws of physics. A neuron fires when electrical and chemical signals cross specific thresholds, creating timing based on biological networks and meaning. You exist within both systems simultaneously. You're subject to the time of the universe, the rotation of Earth, the flow of entropy, all the immutable laws of physics. But you also inhabit your own personal sense of time, a time measured in breaths, reactions, expectations, and experiences. That internal sense of time doesn't disappear when you fall asleep. It reconfigures itself, adapts to new circumstances. Dreams provide the clearest evidence of this. Even in dramatically altered states of consciousness, your brain continues creating time, not because it has to, but because it needs to. Time, for the mind, serves as fundamental structure, a way to link events together, a method for finding order within the chaos of memory and experience. Without some sense of time, you couldn't understand cause and effect. You couldn't construct narratives about your life. You couldn't find meaning in the sequence of events that make up your existence. This is why time emerges even when everything else familiar disappears during dreams. It represents one of the mind's most basic frameworks for making sense of reality, so essential that consciousness itself seems unable to function without it. The moon sits up there, about 238,000 miles away from us, completely unaware of its own existence. It has no nervous system, no brain tissue, no way to process information about itself or anything else. When you stare at it on a clear night, you're looking at a chunk of rock and metal that formed roughly 4.5 billion years ago, probably when a Mars-sized object smashed into the early Earth. That collision threw debris into orbit, and gravity slowly pulled the pieces together into what we see today. The moon doesn't experience this history, doesn't remember the impact, doesn't know it's made of the same basic elements as our planet. It just exists, following the same orbital path it's traced for billions of years. Here's something fascinating about lunar cycles. The moon takes exactly 27.3 days to orbit Earth, but it takes 29.5 days to go through all its visible phases. That's because Earth is also moving around the sun, so the moon has to travel a little extra distance to line up the same way with sunlight. Ancient civilizations figured this out without telescopes, without computers, just by watching the sky night after night. They used these patterns to create the first calendars, to predict tides, to time their planting seasons. The word month comes from moon, and dozens of languages have similar connections, but the moon wasn't trying to help them, wasn't offering itself as a cosmic timepiece. It was just following physics, the gravitational dance between three celestial bodies. Think about what the moon actually experiences, if we can even use that word. There's no atmosphere up there, so no weather, no sound, no protection from radiation. The surface temperature swings from 250 degrees Fahrenheit in sunlight to minus 250 in shadow. Meteorites constantly pepper the landscape, creating new craters, grinding rocks into fine dust. During a lunar day, which lasts about 29 Earth days, the sun slowly crawls across the sky, then disappears for another 29 days of darkness. But the moon doesn't feel hot or cold, doesn't notice light or shadow, doesn't experience the passage of time. It's just matter, responding to forces, absorbing energy, reflecting photons back toward Earth. Meanwhile, down here, we've built entire mythologies around lunar phases. Werewolves, lunacy, romance, menstrual cycles, agricultural timing, religious ceremonies. Every human culture has moon stories, moon gods, moon rituals. We see patterns in something that has no awareness of creating patterns. We find meaning in something that operates purely through mechanical processes. The tides offer another example of this strange relationship. Twice a day, the moon's gravity pulls on Earth's oceans, creating high and low tides that coastal creatures have evolved to depend on. Crabs time their reproduction to lunar cycles. Corals spawn according to moon phases. Sea turtles use moonlight to navigate after hatching. Entire ecosystems organize themselves around lunar rhythms, but the moon doesn't know it's orchestrating anything. It's simply massive enough that its gravitational field affects water on Earth. The pull is strongest when sun, moon, and Earth align, creating spring tides. When they're at right angles, we get weaker, neap tides. Ancient peoples noticed these connections, started treating the moon as a living force, a deity with intentions and moods. They weren't wrong to see the connections, but they were projecting consciousness onto something that operates like a clockwork mechanism. The moon influences Earth through gravity, not through choice or awareness. Modern physics has revealed even stranger aspects of cosmic time. Einstein showed us that time itself can stretch and compress depending on gravity and velocity. An astronaut on the moon actually ages slightly faster than someone on Earth because they're in a weaker gravitational field. The difference is tiny, about 38 microseconds per day, but it's measurable with precise clocks. This means time isn't the steady universal flow that our brains imagine. It's relative, flexible, dependent on where you are and how fast you're moving. The moon experiences time differently than we do. The difference is so small that even if the moon could think, it probably wouldn't notice. Quantum mechanics adds another layer of weirdness. Some interpretations suggest that reality remains uncertain, suspended in multiple possible states, until something observes or measures it. This doesn't mean consciousness creates reality, but it might mean that interaction, measurement, observation play a role in determining what actually happens from moment to moment. The moon probably doesn't qualify as an observer in this sense, since observation in quantum mechanics usually means interaction between particles, not conscious awareness. But it raises interesting questions about what time means in an unobserved universe, where the moments can exist without something to distinguish between them. Meanwhile, back in everyday experience, we use the moon as a reference point for organizing our lives. Lunar calendars still govern religious holidays, agricultural practices, fishing schedules. The Islamic calendar follows moon phases, creating years that drift relative to solar seasons. Jewish holidays shift dates on solar calendars, but stay fixed relative to lunar months. Even our modern solar calendar shows lunar influence. The word calendar comes from Latin calendae, referring to the first day of each lunar month, when debts were due in ancient Rome. We've layered solar precision on top of lunar intuition, creating hybrid systems that track both Earth's orbit around the Sun and the Moon's orbit around Earth. Sleep researchers have found that human sleep patterns sometimes correlate with lunar cycles. Though the effect is subtle and controversial, some people seem to sleep less during full moons, possibly because of increased brightness, possibly because of evolutionary programming from ancestors who were more active during bright nights. But correlation isn't causation, and the moon isn't deliberately affecting our sleep schedules. It's just reflecting sunlight, the same thing it's done for billions of years. We're the ones interpreting that reflected light as meaningful, as connected to our biological rhythms, as worth paying attention to. This creates a fascinating paradox about the nature of time and meaning. The universe operates according to physical laws that don't require interpretation. Gravity works the same way whether anyone understands it or not. The moon orbits Earth according to mathematical principles that existed long before mathematics was invented. But meaningful time, the kind that shapes cultures and personal experiences, only exists when conscious beings engage with physical patterns and decide they matter. We take the moon's regular cycles and transform them into calendars, into poetry, into navigation tools, into symbols of change and constancy. The moon becomes temporally significant, not because it chooses to be, but because we have the capacity to recognize patterns, to remember previous cycles, to anticipate future ones. We're pattern recognition machines, living in a universe full of regular, predictable processes. Without minds to interpret them, these processes would continue indefinitely, but they wouldn't constitute time in any meaningful sense. There would just be motion, change, cause, and effect, but no past to remember, no future to anticipate, no present moment to experience. Time requires both physical change and conscious awareness of that change. So we find ourselves in this strange position, creatures who experience time subjectively, while living in a universe that operates according to objective, timeless laws. The moon doesn't know it's night, doesn't know it's the moon, doesn't know anything at all, but its existence gives structure to our experience of duration, change, and cycles. Perhaps that's enough. This collaboration between mindless physical processes and meaning-making consciousness. We don't need the moon to be aware for it to serve as our timekeeper, our night light, our symbol of constancy in an uncertain world. We just need it to keep following its orbit, while we keep watching, interpreting, finding significance in its silent journey through space. Everything you experience happens right here, in this precise instant. Your thoughts, your feelings, every sensation flows through what we call the present moment. But when you really think about it, what exactly is this moment we live in? It feels solid, like a clear boundary that separates what already happened from what might come next. The present seems like a razor-sharp edge, cutting cleanly between before and after. You exist there. You make choices there. You form memories there. Everything else, the past and future, they feel distant somehow. The past is finished, locked away. The future hasn't arrived yet. Only now feels real, feels immediate. But here's where things get strange. That solid feeling moment, it won't sit still. You can't grab it, can't freeze it in place. The instant you try to point at now, it's already slipped away, already become part of yesterday. Even saying the word now takes time, and by the end of that word, the beginning is already history. Physics doesn't really care about our sense of now. The fundamental equations that describe how things move, how forces work, they treat time like any other measurement. Time becomes just another coordinate, like height or width. There's no special dot on the timeline marked, "This is now." The mathematics works the same whether we're talking about something that happened yesterday or something that happened a million years ago. Einstein's relativity makes this even more puzzling. What counts as now for you might not be now for someone else. If you're moving fast enough, events that seem simultaneous to you could happen at different times for another observer. This isn't just about clocks running slow or fast. It's about the actual structure of space and time itself. There's no universal now that everyone shares. Yet you still wake up each morning, feeling like you're living in a specific moment. You move through time, one step at a time, like watching a movie frame by frame. Your memories trail behind you, your plans stretch ahead, but everything you actually experience happens in this incredibly narrow window. Your brain doesn't process things instantly though. When something happens around you, it takes a few hundred milliseconds for your consciousness to actually register it. Your nervous system has to gather all the signals, sort through them, clean them up, and then present you with what it thinks is happening now. By the time you're aware of something, it's already slightly in the past. You're constantly playing catch-up with reality. This doesn't mean your experience is false or wrong. It just means it's constructed, assembled by your brain from pieces of information. Just like how your brain creates your sense of color or depth, it also creates your sense of the present moment. And like those other senses, it works well enough for everyday life. But it's not perfect. The feeling of now can shift dramatically, depending on what's happening to you. When you're absorbed in something interesting, hours can feel like minutes. When you're bored or waiting anxiously, seconds can stretch like hours. The external world hasn't changed its pace, but your brain's processing of time has shifted gears. Your brain even adjusts what you perceive to make the present moment feel coherent. If you hear a sound and see something at slightly different times, your brain often tweaks your perception to make them seem simultaneous. It creates a unified sense of now, even if it has to bend the timing a little bit. This coherence matters deeply for how you function. Your sense of being alive right now doesn't depend on perfect timing. It depends on continuity. You need a smooth stream of experience that flows logically from one moment to the next. You don't experience now as a mathematical point, but as a brief interval, a kind of rolling present that's always updating itself. Psychologists call this the specious present, the minimum chunk of time your brain processes as a single experience. It's usually less than a second, but that tiny window is crucial. That's where perception becomes action, where separate events get woven into meaningful patterns. That's your working definition of now. The boundaries of this window aren't fixed though. When you're in danger, your sense of time contracts. Everything seems to slow down, giving you more processing power for quick decisions. When you're relaxed, the window expands and moments feel more spacious. You don't consciously control this. It's built into how your nervous system responds to different situations. Sometimes your brain even reorders events to make better sense of them. When you touch something hot, signals about pressure and temperature travel to your brain at different speeds, but your brain synchronizes them, backdating one signal to match the other. So your sense of immediate experience is partly a reconstruction, a story your brain tells about what just happened. You don't notice this editing process because you live inside the final product. But it means that now, as you experience it, isn't a simple recording of the external world. It's more like a best guess, a composite image assembled from multiple sources, yet it feels absolutely solid and real. This feeling of solidity drives everything you do. It makes choice possible, allows you to plan, give structure to your life. Without a sense of now, you couldn't form memories properly. You wouldn't know when something happened relative to other events. You wouldn't know when to act or react. But from physics perspective, particles don't need a sense of now to function. They just interact according to forces and fields. Time is simply a parameter in the equations, not a moment or perspective, just a label. There's a fundamental mismatch between how we experience time and how it actually behaves at the deepest level. Some theories suggest that now is an illusion, that consciousness just moves through a static four-dimensional structure where all times exist equally. We feel the present because we happen to be located at a particular point in this structure, like passengers on a train that only moves forward, even though the entire track already exists. But this explanation raises its own questions. If now is an illusion, why do we need such a convincing one? Illusions usually serve some purpose. So what function does our sense of the present serve? Maybe it's not really an illusion at all. Maybe it's a byproduct of how conscious systems process information. Any system that needs to compare new input with stored memories and future predictions needs some kind of reference point. Now becomes a workspace where incoming data gets merged with internal models. You need this workspace to perceive change, to sense movement, to learn from experience. But the workspace doesn't stay still. Your system keeps updating, new input keeps flowing in, and the frame of reference keeps rolling forward. So now keeps shifting, not because time itself moves, but because the system that creates the sense of now, your brain, your body, your attention, is always changing. This doesn't make now meaningless. It makes it dynamic, a moving balance point where different streams of information briefly converge. That convergence is what allows you to make decisions. You can't act in the past. You can't act in the future. You can only act within the window your system defines as now, and then that window moves on. The now doesn't stay, but it leaves something behind. It leaves structure, memory, traces of having existed. In that record, time builds itself up, one frame at a time. Each moment of now becomes the foundation for the next, creating the continuous flow of experience that makes up a conscious life. Every time you step off a long flight, your body tells you something strange. The sun might be shining, but inside you feel like it should be midnight. Your watch shows one thing, your tired eyes show another. This familiar confusion we call jet lag hints at something much deeper about the nature of time itself. On Earth, we divide time into neat little boxes. 24 time zones, each 1 hour apart. We pretend that when it's noon in London, it's a specific, absolute noon. But even this simple system reveals a truth we rarely think about. Time isn't really universal, even here on our small planet. Now imagine leaving Earth entirely, not just flying to another continent, but traveling out into the vast emptiness of space. Out there, the whole idea of time zones becomes almost laughable, because time itself starts behaving in ways that seem impossible. Einstein figured this out more than a century ago. Time, he realized, isn't the steady tick-tick-tick we imagine. It's more like a river that flows at different speeds depending on where you are. If you're moving very fast, your personal time slows down compared to someone standing still. If you're near something incredibly massive, like a star or a planet, gravity actually stretches your time. This isn't just theory. The satellites orbiting above us right now experience time differently than we do down here. They're moving faster, and they're further from Earth's gravitational pull. Both of these things change how their clocks tick. Engineers have to constantly adjust for this, or else your phone's GPS would be off by miles. Think about what this really means. Two identical clocks, built in the same factory, will tick at different rates, just because one is on the ground and the other is in orbit. Time itself is flowing differently for each of them. Now scale this up to the cosmos. Out there, near a black hole, time becomes almost unrecognizable. A clock hovering just outside a black hole's event horizon would tick so slowly that from our perspective, it would nearly stop. From the clock's point of view, though, everything feels perfectly normal. 1 second still feels like 1 second, but compared to clocks far away, it's crawling through time. This creates something profound and unsettling. There's no master clock in the universe, no cosmic timekeeper that everyone can agree on. Two astronauts traveling at different speeds through space will literally experience different amounts of time between the same events. When they meet up again, they might disagree about how long their journey took. Both would be right. Even stranger, events that seem to happen at the same time for one observer might not be simultaneous for another. Imagine two distant stars exploding. Depending on where you are and how fast you're moving, you might see them explode at the same moment. But someone else somewhere else might see one explosion happen clearly before the other. Neither of you is wrong. This shatters our everyday notion of now. If what's happening right now for you isn't the same as what's happening right now for me, then what does now even mean? On Earth, we mostly ignore these differences because they're tiny. We synchronize our clocks and pretend there's one universal timeline, forgetting to meetings and catching trains. This works fine. But out in the cosmos, this pretense completely breaks down. Different observers don't just have their clocks set differently. They have clocks that tick at fundamentally different rates. Space doesn't have time zones like Earth does. It has something much weirder: personal timelines. This leads to remarkable possibilities. Two people could leave Earth, take different paths through space, and return having aged different amounts. Not because one forgot to wind their watch, but because they literally experienced less time. The famous twin paradox isn't just a thought experiment anymore. We've seen similar effects in particle accelerators and with atomic clocks. Consider what this means when you look up at the night sky. That light from distant stars didn't just travel through space to reach you, it traveled through time. The star you're seeing might have exploded millions of years ago, but you're just getting the news now. Every star, every galaxy, every point of light is showing you its past, not its present. The cosmic microwave background, that faint glow left over from the early universe, comes from a time nearly 14 billion years ago, when atoms first formed. When you detect this radiation, you're literally seeing the universe as it was in its infancy. The sky isn't a photograph of what's happening now, it's a museum of what happened then. This creates a beautiful and strange situation. There's no universal now stretching across the cosmos. Just countless local moments, each one valid, each one real, connected by signals that take time to travel between them. Light, the fastest thing in the universe, is still slow on cosmic scales. Scientists do have a way to define something like cosmic time. They imagine a theoretical observer who's perfectly still relative to the expansion of the universe itself. This observer would have a kind of standard cosmic clock, but no real observer ever matches this perfectly. It's useful for calculations, but in practice, everyone experiences their own version of time. The further you travel from Earth, the less meaningful it becomes to ask, what time is it there? There's no shared schedule, no synchronized moment, when things happen everywhere at once. Just individual histories, each one carved out by motion and gravity and position. Yet somehow, despite all this chaos, structure emerges. Stars still form in predictable ways. Galaxies still rotate. Black holes still grow. The universe follows patterns, but these patterns don't unfold everywhere simultaneously. There's no cosmic metronome keeping everything in sync. So yes, the universe has time zones, but they're not lines drawn on a map. They're dynamic, flowing regions shaped by mass and energy. Every object moves through its own personal time zone. You're living in one shaped by Earth's gravity, by the sun's pull, by our galaxy's motion through space. But that's just one of infinitely many such zones. This makes time deeply personal, not just in the psychological sense where minutes can feel like hours when you're bored, but in a physical sense. Each particle, each planet, each person follows a unique path through space-time, and each path defines its own rhythm of aging, of change, of existence. You can synchronize two watches, but you can't force the universe to agree on what now means everywhere. When we look at distant galaxies and wonder what's happening there right now, we're really asking about events that occurred long ago. The light carries old news, arriving fashionably late to a party that started eons ago. Time zones in space aren't zones at all, they're flows, currents in the river of space-time, each one carrying its passengers at their own unique pace through the cosmos. In this vast universe, time isn't just relative, it's intimate, personal. A private conversation between each observer and the fabric of reality itself. Time flows around us in patterns that seem almost deliberate. Stars ignite, burn bright, then fade away. Planets trace their endless circles through space. Galaxies rotate with a rhythm that spans millions of years. These cycles repeat with such precision that we can predict eclipses centuries in advance. Build atomic clocks that won't lose a second for eons. The predictability makes it tempting to think there's some grand schedule at work. Some cosmic timekeeper, marking off events like appointments in an infinite calendar. But when you look closer, something interesting emerges. The universe doesn't actually keep time, at least not the way we imagine it does. Consider how a star is born. Deep in a cloud of hydrogen, atoms drift closer together, pressure builds, temperature rises. Eventually, conditions reach a critical point where fusion begins. The star ignites, not because some cosmic alarm clock went off, but because physics demanded it. The threshold was crossed. The event happened naturally, inevitably, but without any external scheduling. This threshold principle governs almost everything in space. A black hole forms when a massive star collapses beyond a certain radius. Not earlier, not later, just when the conditions are right. A comet returns to the inner solar system when its orbit brings it close again, following the mathematics of gravity and motion, not following a predetermined timetable. What we call patterns are really just the consequences of physical laws playing out across vast scales of time and space. Gravity pulls matter together in predictable ways. Energy flows from hot to cold, according to thermodynamics. Quantum fields fluctuate within known parameters. These aren't schedules, they're constraints, boundaries that shape how events unfold. The difference matters more than you might think. A schedule implies awareness, intention, someone or something keeping track of what comes next. The universe operates without that kind of forward planning. It doesn't anticipate future events. It doesn't wait for the right moment. It simply continues, moment by moment, following the rules that govern matter and energy. Even our most reliable cosmic timekeepers aren't perfect. Pulsars, those incredibly dense neutron stars, flash with such regularity that astronomers use them like lighthouse beacons across the galaxy. Their pulses arrive so consistently that we can detect tiny variations in their timing. But over long periods, even pulsars slow down. Their rotation gradually decreases. The schedule drifts. This brings us to something profound about randomness in nature. Radioactive decay follows statistical laws that let us predict how many atoms will break apart in a given time period. But we can never know which specific atoms will decay, when. The universe contains genuine uncertainty, not chaos, but built-in unpredictability that no amount of planning could eliminate. Our human need for schedules comes from living in groups, from having goals and needs that require coordination. We wake when the sun rises, count days by lunar cycles, mark seasons by the Earth's orbit around our star, These natural rhythms become the foundation for our calendars, our clocks, our entire system of organizing time. But step outside our planet, and those divisions lose their meaning. A year is just how long it takes Earth to complete one orbit. Other planets have different years. Some take decades, others mere days. There's no universal standard, no cosmic definition of what constitutes a proper year. The same applies to smaller units. Hours and minutes exist because we divided the day into convenient portions. Seconds were originally fractions of Earth's rotation, though now we define them more precisely using atomic transitions. These measurements work wonderfully for human purposes, but they're essentially arbitrary from the universe's perspective. Think about what happens in the depths of space, far from any star or planet. Time still passes there, but there are no regular cycles to mark its passage. No sunrise, no seasons, no obvious rhythms, just a gradual expansion of space itself, carrying galaxies apart at an ever-increasing rate. Even that expansion isn't following a schedule. It's responding to the mysterious force we call dark energy. The cosmic microwave background, that faint afterglow of the Big Bang, tells us the universe was once much hotter and denser. As space expanded, that ancient light cooled and stretched. We can trace this process backward to the very early universe and project it forward into the distant future. But even here, we're not following a predetermined timeline. We're tracking the consequences of physical processes. Some of these processes happen incredibly fast. When particles collide in the cores of stars, nuclear reactions occur in tiny fractions of a second. Other changes take billions of years. Mountains rise grain by grain, continuance drift centimeters at a time. The universe operates on every timescale imaginable, with no preference for human-friendly durations. This creates an interesting philosophical question about the nature of time itself. We experience time as flowing from past to future, carrying us along like passengers on a river. But physics suggests time might be more like a landscape, where past and future are simply different locations. Events don't happen in time so much as they exist at particular coordinates in space-time. From this perspective, asking whether the universe keeps a schedule becomes almost meaningless. A schedule assumes time flows and events occur in sequence, but if all moments exist equally, if the past and future are as real as the present, then the universe doesn't keep time any more than a map keeps track of your journey. Yet here we are, conscious beings who do experience time's flow, who do need schedules to coordinate our activities. We evolved in a world of cycles, sunrise and sunset, seasons and tides. Our brains are wired to detect patterns, to anticipate what comes next, to plan for future events. In a sense, we're time-keeping creatures living in a universe that doesn't keep time. This mismatch creates both opportunities and limitations. We can use the predictable aspects of nature, the reliable patterns of planetary motion and atomic behavior, to build incredibly precise timepieces. We can schedule spacecraft to arrive at distant planets years after launch. We can predict when specific stars will exhaust their fuel and explode as supernovae, but we also run up against the universe's fundamental unpredictability. Quantum mechanics shows us that some events are genuinely random, not just difficult to predict. Weather systems become chaotic over periods of weeks. Evolution takes unexpected turns. Even the laws of physics might change over cosmic timescales. Looking toward the far future, our ability to maintain schedules will gradually diminish. As stars burn out and aren't replaced, the universe will become darker and colder. Fewer processes will generate the regular patterns we use to mark time. Eventually, even protons might decay, eliminating the last structures that could support complex systems. In that distant era, if any conscious observers still exist, they won't have access to the cosmic clocks we rely on today. No stellar cycles, no radioactive decay, no planetary orbits. Time will still pass, but it will be increasingly difficult to measure or divide into meaningful intervals. Perhaps that's the ultimate lesson about schedules and cosmic time. The patterns we use to organize our lives are temporary features of a young, energetic universe. They're not fundamental properties of reality, just convenient regularities that happen to exist during this particular epoch. For now, though, we live in an age of abundant timekeepers. The universe provides plenty of rhythms to build our schedules around. Even if it doesn't follow any master schedule itself, we can continue planning our days, our years, our lifetimes, using the reliable patterns of nature as our guide, while remembering that those patterns are gifts of physics, not promises from the cosmos. Entropy governs everything around us, driving systems from order toward chaos, from useful energy toward equilibrium. Heat spreads out, motion gradually slows down, and eventually we arrive at something called heat death. This represents the universe's slow fade into uniformity, where nothing dramatic happens anymore. Just fewer and fewer changes stretched across impossibly long time scales. Stars will burn out completely. Black holes will evaporate into nothing. The last remaining particles will interact one final time. After that, there's simply nothing left to change. Without change, without motion, time as we experience it essentially vanishes. You could still assign mathematical coordinates to moments, still define that this happened after that in some abstract sense. But those numbers would stop meaning anything real. Think about what time actually is for a moment. We imagine it as this constant background, the stage where everything unfolds. But physics suggests time might be more fragile than we assume. Some theories propose that time, like matter and energy, had a beginning and could have an ending too. The Big Bang wasn't just when matter started existing, it marked the birth of time itself. Before that moment, the word before might not even apply. Our equations completely break down when we try to look further back. The earliest moment we can define represents the start of spacetime as one unified thing. Current data shows the universe's expansion is actually accelerating, driven by this mysterious force we call dark energy. Space isn't just growing, it's growing faster over time. This makes certain dramatic endings unlikely, but it opens up other strange possibilities. In one scenario called the Big Rip, dark energy doesn't just expand space, it literally tears everything apart. First galaxies drift away from each other, then stars separate within galaxies, then atoms themselves get pulled apart. Eventually, even space-time could be shredded. The expansion rate would overwhelm every other force in nature. But here's where things get really interesting. Some approaches in physics, like loop quantum gravity, suggest time might not be fundamental at all. Instead, time could emerge from deeper relationships between things. At the smallest possible scales, there might be no smooth, continuous time, just a series of configurations connected by statistical rules. If that's true, then time isn't something that flows like a river or ticks like a clock. It's something we perceive when certain conditions are met, when systems interact with each other, when patterns can unfold, when memory becomes possible, and if those conditions disappear, if systems lose all contrast or collapse into perfect sameness, then time as an emergent phenomenon simply ends. Not because something destroyed it, but because it's no longer needed. Like a tool that gets set down after the job is finished, black holes give us a glimpse of how flexible time really is. Near the event horizon, time slows down dramatically compared to the outside world. From a distant observer's perspective, an object falling in seems to freeze just before crossing that boundary. The object experiences time normally from its own point of view, but to everyone else watching, it vanishes into a complete standstill. This shows us that time isn't universal or constant. It bends, stretches, slows down, and possibly ends, but not everywhere at once. Different places in the universe can experience completely different relationships with time. Consider another possibility. Maybe time never truly ends, but simply becomes irrelevant. Picture a future where the universe has stretched out so much, become so sparse, that no meaningful interactions happen for quadrillions upon quadrillions of years. Particles might still exist somewhere out there. Time might still tick in some abstract mathematical sense. But with no observers left, no clocks running, no events occurring. Who would be around to say what time even means? That's not quite the same as time stopping completely, but it represents a kind of practical vanishing. The loss of time as anything that matters to real experience. Right here, right now, time continues holding together the sequence of everything we do. It gives structure to our memories, to motion, to life itself, but whether it will last forever depends entirely on what time actually is at its core. If time is fundamental, built into the absolute bedrock of physics itself, then maybe it keeps going regardless of what happens to all the stuff inside the universe. If time is emergent, arising from matter and energy in motion, then maybe it fades away like any other pattern, when the pieces spread too far apart to interact. And if time is only an illusion, a trick our brains play on us, then maybe it never really existed to begin with. Maybe only the changes existed, only the differences, only the things we compare, and the moments we manage to remember. Perhaps we should ask a different question entirely. Will change ever end? Because if the answer to that question is yes, then that's precisely when time ends too. Not with some dramatic announcement or cosmic alarm bell, but quietly, slowly, with the very last change getting undone by perfect, eternal stillness. The universe might fade into a state where one moment becomes completely indistinguishable from the next, where nothing marks the passage of what we used to call time, where the background against which everything happened simply dissolves into uniformity. It's a strange thought that time itself could be temporary. We're so accustomed to thinking of it as permanent, as the one thing that definitely keeps going no matter what else falls apart. But the deeper we look into physics, the more we find that even our most basic assumptions about reality might be much more fragile than they appear. Time surrounds us in ways we barely notice. Every breath you take happens in sequence, one after another, never all at once. Your heartbeat follows this same pattern, creating rhythm from what could be chaos. Scientists have spent centuries trying to understand what this thing actually is, this invisible framework that seems to hold everything together. Think about memory for a moment. You remember yesterday, but not tomorrow. This asymmetry tells us something profound about how time works. Memory itself is really just patterns in your brain, arrangements of molecules that somehow encode experiences. These patterns change constantly, shifting and updating, creating the story you call your past. Without this biological filing system, time might feel completely different, maybe not even exist as a concept. The universe doesn't actually care about your personal timeline. Stars burn for billions of years, completely indifferent to human schedules. Light from distant galaxies travels for so long that what you see in the night sky is ancient history, photons that began their journey before Earth even existed. This cosmic perspective makes our daily concerns seem tiny, almost irrelevant. But here's where it gets interesting. Physics suggests that time might not flow at all. Einstein showed us that simultaneity is relative, meaning events that seem to happen at the same time for you might occur in different orders for someone moving at high speed. This challenges our most basic intuitions about reality. What feels like a universal now turns out to be deeply personal, tied to your specific location and motion through space. Your brain constructs the experience of flowing time from discrete moments of awareness. Neuroscientists have found that consciousness isn't continuous, despite how it feels. Instead, it updates in brief snapshots, roughly 10 times per second. Your mind then weaves these snapshots together, creating the illusion of smooth, flowing experience. It's like watching a movie, where individual frames blend into seamless motion. The present moment you're experiencing right now has no fixed duration. Is it a second, a millisecond, or something even shorter? Philosophers have puzzled over this for millennia. The present seems to exist, but it has no measurable thickness. As soon as you try to pin it down, it becomes the past. This creates a strange paradox, where the only time that feels real is also the most elusive. Consider how different animals might experience time. A hummingbird's world runs at incredible speed, with wing beats faster than human eyes can follow. Meanwhile, trees operate on seasonal timescales, their responses to environmental changes unfolding over weeks or months. Each creature inhabits its own temporal landscape, shaped by biology and behavior. Time isn't uniform across life, it's deeply personal to each species. Temperature affects how time feels too. When you're cold, chemical reactions in your body slow down, including the neural processes that create your sense of duration. This might explain why time seems to crawl during uncomfortable situations. Your internal clock literally runs at different speeds, depending on your physical state. Fever can make minutes feel like hours, while deep focus can make hours disappear entirely. The arrow of time emerges from entropy, the tendency for organized systems to become more disordered. This is why you can remember the past but not the future, why eggs break but don't spontaneously reassemble. The universe started in an extremely organized state and has been spreading that organization thinner ever since. You exist in this process of cosmic unwinding, a temporary pattern of complexity in an expanding sea of simplicity. Quantum mechanics adds another layer of strangeness. At the smaller scales, particles don't follow definite paths through time. Instead, they exist in superpositions, potentially taking multiple routes simultaneously until something forces them to choose. This suggests that time itself might be fuzzy at the quantum level, becoming definite only when we zoom out to larger scales. Reality might be far weirder than our everyday experience suggests. Your sense of time changes throughout your life. Children often feel that summers last forever, while adults watch years blur together. This happens because new experiences create more distinct memories, making time periods feel longer in retrospect. As you age and fall into routines, fewer unique moments stand out, causing time to seem accelerated. Your perception of duration depends more on memory than on actual clock time. Sleep offers a fascinating window into time's mysteries. During dreams, chronology becomes fluid. You might experience elaborate scenarios that feel like they last hours, but occur during brief REM cycles. Sometimes you wake with no sense of how much time has passed. Sleep temporarily disconnects you from time's normal flow, revealing how dependent your temporal experience is on conscious awareness. Time dilation isn't just theoretical, it affects GPS satellites orbiting Earth. These satellites experience time slightly faster than we do on the surface, due to weaker gravity and their orbital motion. Without correcting for these effects, GPS would accumulate errors of several miles per day. Time really does run differently, depending on where you are and how fast you're moving. This isn't science fiction, it's engineering reality. The question of whether time travel is possible depends on what you mean by time. If time is just another dimension like space, then maybe you could move through it in different directions. But if time is the unfolding of cause and effect, then traveling backwards might be logically impossible. Even if you could visit the past, you might not be able to change it without creating paradoxes. The nature of time determines what kinds of stories are possible. Perhaps time is best understood, not as something external to you, but as part of what you are. You exist as a process, not a thing, a pattern of change that unfolds through moments. Your identity isn't fixed, it's the ongoing story of how you develop and respond to experience. Time isn't just the stage where your life happens, it's woven into the very fabric of what makes you you.